plan for me. He has spent sleepless nights and he has come up with a plan. Not a good plan, but it's a lot of features. It requires triple the work from me, but who cares? That's like, it's clever. I can't see my fault, but I already only ran it before.
I see. Oh, that's why there's an X.
Figured out
It's the smile.
There you're.
There.
Actually, we didn't have that on the whole time. Actually, now I see. Actually, now we finally understood how to do it.
See, we are not like in showbiz, that's why. But that's the cap.
Summer
Makes movies.
Because I was noticing that post is really great.
This is
That's literally or
really more pieces as he's.
Yeah,
Yeah, this sure.
Would it be okay?
It's a huge amount of work for me.
Matthias.
Processing stuff, editing stuff.
But issue, that's the good shit.
You can see.
You'll go. But definitely, but
Do you
then.
mind if I just?
Yeah, definitely bring it up, definitely bring it up.
I just feel like,
Look, everything is gonna be public. I'm not playing
No,
games. Everyone knowing what I'm doing.
Yeah.
But if like he sees a cut, yeah, it's the third year. it's all-
She just wants to test that.
I hope
they-
it's sent
you
it.
persist to make sure.
Sure. That's.
It
If
says everyone seems to
I
have.
tell the
100
group they were
models.
expecting a third year commitment. but I'm
Yeah,
like,
it sometimes goes dark.
What are they gonna do? I'm not gonna test them.
Yeah, it's weird how that goes. Oh, you're good, you're good.
Okay, great.
Which one's that? You just,
USB-C,
you just connected.
yeah, I mean, I also have HDMI on the other side,
And
but.
this is HDMI.
Yeah, so then the report is the
Oh,
USB-C.
Stocks was-
I could do the HDMI directly.
Ah, directly, okay.
This seems to work. Okay,
Oh,
great,
that looks good, yeah.
yeah. Well, just so we're-
Gambit.
This is the.
Ah, yeah.
We are in the committed people session.
See, the
8:30
thing,
a.m.
I haven't
On
thought of
Saturday.
it. I haven't even checked on the group that I cut when I was expecting.
Another
The third installment, second installment.
All right, I'm
And
sorry.
well, they're gonna cut some of I'm gonna cut postdocs there too.
I just need to plug it back.
I'll tell,
They're
I'll
gonna
tell
cut their summer
Matthias,
salaries.
okay.
Especially if I tell them to, because it's now in the past anyway, we're not gonna do it. Summer salaries.
He's a flight or something.
And he says, if I'm
saying
willing
you're
to
on-
reach out to all the out there commitments,
We might go.
3 years ago, 2 years ago, 1 year from now, and just say, guys, I'm taking down 50% they're not getting. And
So,
take it out of your
yeah, so I'll just tell them that. Switch,
Yeah.
yeah.
Then I can actually afford to give some grants this year.
Okay.
And I need to run that out.
Yeah. This is an interesting idea.
Yeah,
This has merit. I'm gonna run to the bathroom so I can get back. Oh, I got 10 minutes, I think. So,
Yeah, this looks like it's really set up. If there's an indigo page, this, you can always bring it up. The Zoom.
not that I feel I'm going to need it, but simply because I want it, I'm gonna get some coffee.
All right.
As I said, no need, it was.
Well, we are not judging either way.
Test, I let the. Yeah.
You are connected.
Well, yeah, I can
You can disconnect just for a moment.
Soon I have to start time. For like, the first minute is find out.
Which of the two?
Whatever you want, this is HDMI, yeah, this one here.
This has an HDMI.
You can go straight into it, yeah.
Continuous screen locks after a certain number of minutes. It's still security features, but I guess I couldn't block it on the top. We'll find out. That's what I
Looks good, right?
Yeah,
And then,
yeah.
hit play and, should be good, right? Go good to that. Yeah, it looks very good, we got.
Oh, wow.
Very good, yeah,
Good.
he's good.
Fine.
He's very good.
Good.
Okay, perfect. Thanks, Matthias.
All right, now.
Keep the mic.
If you want.
Nobody uses microphone.
Only one person used the content.
But
He speaks softly.
yes, he speaks very soft.
Yeah, All right,
Softly,
we're all
but he
good.
carries a big stick.
You probably don't have to shrink this.
Yeah,
I think it's a bit, it's kind of like very aggressive.
yeah.
Oh,
I think 5 is already
Yeah.
clear side.
yeah, and what you can do is that, you can just tell the speakers that if they want to go and into their question time, it's okay, it's 25 plus 5.
25 plus 5.
But if they want to go 30 minutes.
Okay, okay, yeah, in total, it's like maximum 20 minutes.
No, don't tell them
35.
that. Don't- just say it's 30 minutes, but.
Okay.
Yeah, if we can,
In total.
we don't want to do it.
Yeah, yeah. Usually it's 5 minutes.
But if they want to go on the question, it should be 25 plus 5. But we haven't been following on that.
Yeah, it's.
But that's why we
Yes.
accumulate.
Yes, yes,
Yeah.
small area.
Okay, yeah, so you're all fine.
Okay, so the.
They're all
local
set up,
speaker-
yeah, they're
okay.
all set up.
Nice, nice. And I have a little one to do.
Yeah, so then you can be in the front, you can be. in the
Yeah.
front.
Sure, where do you post the photos?
I will give them to Megan
Ah,
and she will put it on the website.
wow, nice, nice.
So they all will be publicly available. Don't worry.
Yeah, I believe you have taken many nice photos.
Let's see.
Great, great.
It's the most warm in here again, isn't it?
No. But for the rest of my life, I will haunt you. I'll make it my mission.
So they say you're free, you are free not to come, but then I'm free to hunt you for the rest of my life.
You know, both freedoms are available.
Yes, yes, this is a free country. Maybe.
It's not, it was.
Maybe.
There are other countries where the president has to go to jail.
Not yet.
No,
Well.
He's now in court, so.
wasn't he
We didn't
detained?
decide.
Wasn't he detained?
He was detained, yes, he
I
was
think
detained.
But released.
Yeah, then he was set free.
Yeah.
I think shows that the country works.
Well, I don't know if Kim will agree with.
Without any political statement being involved.
We're in the process of electing the new president.
Which will also eventually will be also corrupt.
No.
No, it's opponent.
Oh, okay. Are you gonna confess the crime or not?
We got the spotlight on you. Gotta stay on that edge.
No.
Back.
Welcome to this last day of workshop. For the first session, we have Hooman and Davoudiasl. He will talk to us about these potential reheating Instantons. And
Okay, thank you very much, and thanks to the organizers for inviting me and running such a great workshop. Where I reunited with many of the old friends and new ones, so and thank you for coming, waking up in the middle of the night on a Saturday here. So this is work I did several months ago with one of the students. Us and now is so posted already in the archive. So I guess this audience doesn't need any reminder that the Higgs system's origin is an open question. And very often we try to see where it come from, perhaps it's relatively low mass compared to conceivable scales of physics that we do, which is a version of the hierarchy problem. Like so small compared to some possible use scales. Could there be other scalars that help with this? Most of them are so. All right. I need to be amplified. Sorry.
Oh, where does it go? Can you hear me better? Ah, great. So yes, I just. And maybe this tells us there should be other scalars that help with the hierarchy problem, or the origin of the Higgs comes from them, like you would get in supersymmetry. Could the Higgs be a composite object, as we have been talking about in this workshop? And after more than a decade of searching, still no hint as to what the origin of the Higgs may be. And as you know, the current data is quite consistent with the standard model Higgs picture as an elementary particle. But given that we don't really have any clue, and it seems like it could be an elementary particle as far as we can tell, is there still a role for strong dynamics in shaping the Higgs origins property? So in this talk, I'm going to tell you about a possibility where the Higgs is an elementary particle, but it's potentially set up by strong dynamics. So this picture I'm telling you is not necessarily related to any hierarchy resolution, but it could be. What I would use is just a simple EFT to set up the problem and show how this could happen. But this EFT can potentially come from a model that addresses the little hierarchy. For example, why is Higgs lighter than a reasonably large cutoff where new physics may show up, like 10 TeV. And to show this, we address this in the context of twin Higgs models that many of you probably are familiar with. But if you're not, the basic idea is in the twin Higgs model, it's assumed that there is a mirror standard model sector, and you can achieve Higgs as a pseudo-Goldstone boson, and the UV cutoff the model is around 10 TeV. In this version of the hierarchy resolution, the mirror sector, of course, has all the properties of the standard model, except in a mirror world. And the mirror QCD typically is taken to confine at scales that are small compared to the weak scale. So maybe then they would get GeV scale glue balls, and our Higgs, the standard model Higgs, can potentially decay into these glue balls, which would allow for some signals to be searched for. So, but in this version of what I'm going to talk about, in this version of the twin Higgs, or this general framework that I'm going to present, this confinement scale is taken to be at or above the weak scale. And so you can think of this as a new regime of twin Higgs models where the confinement scale is not near GeV, but it's at or above the weak scale. And it would lend itself to a different kind of phenomenology. So the basic idea is this. Let me just introduce this dimension 6 operator that couples Higgs dagger Higgs to some field strength of some SUN gauge sector, which is not in the standard model. It's a different gauge group. We take it to be SUN. So as long as n is larger than 2, is fine. And of course, this gauge theory has a gauge kinetic term with an initial coupling of G naught, as long as Higgs doesn't have a VEV. So this is the bare sort of kinetic term. After electroweak symmetry breaking, when Higgs gets a VEV, as you can imagine, this kinetic term gets a shift from the VEV of the Higgs. And so the new redefined gauge coupling becomes 1 over G squared as 1 over G naught squared plus this contribution that you can get from this effective field theory. So on general grounds, gauge instantons can then generate a scale gauge instantons of this gauge theory that is roughly some UV scale times the action of the instanton, e to the minus s, and this is the well-known action of a SUN instanton, minus 8 pi squared over G squared. Oh, now it wants to update. Sorry, don't do that. So, and just very simply, if this is the case, this is the new gauge coupling that would have to go to this instanton action. And to the extent that the actual Higgs is fluctuations on top of that background value that redefines this gauge coupling, then you would expect a potential to be generated for the Higgs, which has some mass to the 4th that is generated by this dynamics. But there appears, due to the fact that now Higgs is part of the definition of this gauge coupling, e to the minus 8 pi squared h dagger h over some mass scale that defines the EFT. And if I add now just a quartic to this potential, so let's say that as a possible renormalizable interaction of the Higgs, then I get myself a potential. And this is my point of departure. So there was a quartic by itself would not give you any potential that leads to a VEV, as we know, but with this contribution from this instanton, you get a new potential.
Hooman, don't we know the running of the strong coupling at the weak scale? Because you are modifying it within LHC scales. Yes, the alpha S, you're modifying within.
This is not alpha S. This is a different gauge.
Oh, okay.
This is
not
an
alpha S.
SUN gauge from a dark sector.
It's not QCD.
At all, no. So let me emphasize that. Thank you for asking, because I'm not using instantons of QCD. This is a mirror or hidden sector or dark sector gauge group that in this EFT fashion couples to the Higgs. And you can imagine there are a variety of ways for this to happen. And in particular, twin Higgs is an example. Yes.
And then, sorry. Go ahead.
So you're assuming there are no other light degrees of freedom on the dark sector, like scalars or fermions that you could write that similar.
Right. This is the cleanest version of it that I'm producing that is at the scale that I'm discussing. All those other, there could be like heavy quarks of that hidden SUN gauge theory, but they're integrated out, and perhaps that's how you get this interaction. So now you're in a pure gauge theory, and this is the only operator that has dropped down to us. And all I'm doing is I'm adding a quartic, and then now I have a Higgs potential that I can study.
But why do you forbid H dagger H?
Yeah, in fact, I wanted to ask.
Why is it H dagger H?
You're forbidding a H dagger H treatment.
Right. So you see, it's a ignore master for simplicity. What to the 4?
It's bigger than U0 to the 4, then you're lost.
Right. But for now,
What they are trying to say is that, you have H dagger H in that coupling in front of the gluon, yes? So that's not forbidden, then how can you possibly forbid the H dagger?
No, I agree. And so for simplicity, you can always add it. But you may say, well, but if it's large, it would disrupt all the things you're going to tell me in about a minute. And I'm saying, in general, it can be included, but we are assuming it to be small or either sufficiently tuned. I mean, I'm just trying to show a picture. Or we can assume that there is some symmetries in this underlying theory that actually controls its size, and I can maintain a small size for it, so I can ignore it here.
Yeah, but then how come the other one doesn't control the H dagger H G squared? Yes, the same symmetry.
Yes, whatever makes H dagger H small is gonna make any coupling of H dagger H to anything else small.
Well, then you can assume that it's tuned. How's that?
Okay.
I had a different question. Didn't you say you're gonna take this confinement scale of order 100 GeV?
Yes, generally.
So I'm a little confused why you only focused on the Higgs sector here. In the sense that you could imagine I could have replaced GG with the confinement scale, and then this would be a contribution to the Higgs mass. So shouldn't I be doing confinement and electroweak symmetry rating simultaneously?
Right, and that's going to happen basically. So
The way you phrase it here, it's only a shift to the GG piece.
right. So once Higgs gets a VEV, it will shift this.
Right, but the confinement scales, you're saying is basically the same scale as the VEV.
It's not exactly the same scale as the VEV, but as I will argue, it will come close to those scales. If you just buy this picture that there is a Higgs potential that is, I guess what I'm trying to say is that, for example, this could also be maybe understood by analogy with the Axion, that Axion couples to GG2, and once QC deconfines, it generates a potential for the Axion, which is the usual ones we all have heard about. But here, all I'm trying to say is that if this is the case, and if I just told you that if Higgs gets a background value, it would shift the gauge coupling of this hidden sector SUN, it seems to me that then whatever fluctuation is on top of that background should show up in that potential the same way. I mean, in the same way as in e to the minus 8 pi 1 over g squared, where this part of it now is coming from just the Higgs field. It's now part of the definition. So you can imagine that if you go down to very, very short distances, there is a fluctuation associated with the Higgs that affects this instanton potential, and that's how it shows up. So that's the point of departure. Of course, if
Aren't you assuming confinement scale higher than the weak scale?
it's in that ballpark, yes.
Then before Higgs VEV inject into this potential, already you get like mu to the 4 divided by m squared h dagger h first generated.
Right.
So
I'll show you this in a second.
okay, you don't seem to have a regime where there is a back reaction the other way around.
Well, so let me go on if you don't mind, and then
Can I ask questions? Why is this instanton effect? This doesn't look like instanton effect.
this doesn't look like an instanton.
No, it's just a gauge coupling depend on H dagger. If a confinement scale or lambda fold, and confinement scale depend on the Higgs.
Well, again, I think maybe I'm not either saying it correctly, or maybe you're pointing to something I'm not quite grasping. I'm saying if this coupling is there, you should really think about as the gauge coupling of.
But this doesn't look like an instanton effect.
Okay, so how would you agree that this would be an instanton generated potential?
Not the instanton effect.
No.
Just the gauge coupling depend on Higgs, and the dynamic scale depend on the Higgs, and hence you have a lambda folds that depend on the Higgs. In particular, I think the form will be fine, but this should depend on beta function of the SUN. Just a small point, just change the coefficients.
But you would agree that such a form would appear.
This form will appear, but this doesn't look like an instant effect.
Okay, so maybe up to semantics and what we call this, we can agree that this would appear, and that's all I need. So Thank you. But either instanton or something coming from the confining properties of this gauge group. So I guess time flies.
It's gonna be fun.
I know. So anyway, we continue. So let me just get the vacuum solution. Look, the potential I wrote down, I think any one of you in 10 minutes can work it out and find out that, if I want to minimize this potential, I define this y, which is Vev squared over 4m squared, and this is the equation that would give it. And it turns out, where r is defined as this, these are the parameters of the potential, the quartic, the mass scale of the potential, the mass scale of the AFT. And this actually turns out to be the solution to this problem is given by Lambert W naught function. Johann Lambert actually was also the first to prove that pi was irrational. So, good person to keep in mind. And so you get a solution. So just in case you're interested. Of course, the above ignores the back reaction of Vev on this solution. So if you want to, that is to say, once you have a back reaction, the value of the gauge field changes, which makes it smaller, which means that the confinement comes down. So the mass scale of that potential would drop down a little bit to some extent. But then if you want to account for the back reaction, what you would get is that these are the new parameters that you have to take into account for this W naught function, and then also this new scale is defined by this relationship that hopefully you can read. But up to those things, this proposed Higgs potential has 3 parameters: the mu naught scale overall, the EFT scale, and the quartic. But note, please, that this quartic is not what you would call the quartic. This is not the real actual coupling of the Higgs. You have to derive those. And so we first actually require that you get the right Higgs mass, about 125 GeV, which is given by the second derivative of this potential. And once you do that, one can have lambda mu as a function of this m. And as I advertised before, this mu naught parameter, which is the overall scale of this potential, turns out for a variety of, as you can see, it looks like I guess Nike. So it's for various values of m has a certain shape. But the point is that it's all around the weak scale. And as you may expect, as m gets larger and larger, this actually approaches the quartic coupling value of the standard model, if you remember what it is. But so that shows the right behaviors. And so now you can actually ask yourself, what is this Higgs self-coupling in this theory? It's defined by these derivatives of the potential, as you know. And so again, as the effective scale of that EFT gets larger and larger, these couplings approach their standard model values. And you can see that, for example, as long as this effective theory that I wrote down has a scale that is slightly smaller than 3 TeV, you can get a 10% deviation from the standard model, roughly, compared to the triple Higgs coupling of the standard model. So that's a signature of this for these kinds of mass scales. Then this could be detectable in Higgs double production at a future collider, for example, as has been discussed in various reports, especially.
So this is a deviation fundamentally due to whatever the UV completion is connecting H dagger H with GG. Yes.
I'm saying if you took that EFT that I wrote down and the potential, and then computed what are the triple Higgs couplings, you would get an expression that for low values of m has a deviation from what you would expect the actual triple Higgs coupling be in the standard model.
It's just a different potential.
Right, it's a different
Potentially,
potential.
it's a different Higgs potential, so the relations will be different.
But
Of course, but there's also a glue ball in your spectrum.
glue ball?
Right.
No, glue balls, as I would argue, are above the Higgs mass.
They're all the Higgs mass, but there would still be a mixing between,
Yes,
between
actually,
the Higgs.
Yeah, but with
Wouldn't that effect be larger than these UV completion contributions?
the effect of glue ball?
The effect of glue ball mixing with the Higgs.
And you mean just generating a
Because you had GG and H dagger H, and so I just expand and I would have a blue ball 0++ mixing.
right, which I will discuss.
Oh, okay, sorry.
So what I'm saying, if you just take that potential and ask yourself, what is the triple Higgs coupling in this model? This is what you would get. And as n gets larger and larger, they approach their standard model prediction values. That's all I'm saying. But in my remaining, so the one thing that you might want to make sure is that because I showed that these couplings are in principle smaller than their standard model value, you want to make sure that there is a stability of the potential as you go up. And so it turns out in this model, the running of lambda, this lambda quartic that I have in the theory. So, well, of course, this lambda is not the triple Higgs coupling the same way it's in the standard model or the quartic Higgs coupling. It's just this parameter. But you want to make sure that whatever I did, this lambda stays sort of stable, given that it could have a different value compared to the standard model value. But this running is exactly the same as the standard model because there are no new states that come into the running. Up to very, very tiny Higgs mixing, which I will discuss, I guess, if that's something you're worried about. The point is, if you plot it, you'll see that for if M is 2 TeV, 3 TeV, 4 TeV, or 6 TeV, all these, this quartic parameter of my Lagrangian stays positive. So there is no issue, at least up to any scale of the EFT I have. And after that, a new system, a new theory shows up. So we have to calculate in that. Now, let me talk a little bit about the early universe part of this. So let's consider the early universe at temperatures larger than hundreds of GeV, where you might want to do some model building or baryogenesis or whatever you like to do in that time. Now, ask yourself, given the EFT I had, just that EFT, what is the decoupling temperature of that EFT? And by simple dimensional analysis, you can convince yourself is given by this. And it turns out that as long as this M that I chose for the EFT is less than 10 TeV, the decoupling temperature is less than 0.1 GeV, 0.2 GeV. So it means that for these temperatures, the hidden gluons and whatever is there is in equilibrium. And so, of course, as you go well above the weak scale, because this theory is an SUN, it gets, well, assuming that it doesn't have too many degrees of freedom, it becomes asymptotically free. And so the instanton or confinement effects become negligible. And VH then would be dominated by quartic, which means that at the end of the day, you will go back to a symmetric phase of electroweak symmetry break. I mean, electroweak symmetry being restored as you want in general. And even thermal effects of T squared H dagger would only help this situation. So basically, as you go up in temperature, you expect electroweak symmetry to be restored. But the thing is that for these kinds of temperatures, as you get close to the weak scale, hundreds of GeV, the way this effective theory is set up, the only thing you have are pure glue, is only pure glue, which means that this phase transition that confines these hidden gluons is actually first order, as is generally accepted for a pure Yang-Mills theory to be, which means that electroweak symmetry breaking, which is initiated by the confinement and generation of this potential, is closely preceded by a first order phase transition, which could give rise to potentially observable gravitational waves. As you can see, for example, if the temperatures are around a few hundred, GeV, there are possibilities. Although, this may not be the most recent plot. So, but in general, we expect that some of these, pulse or timing arrays or space observatories possibly can detect such gravitational waves coming from first order phase transition. And I'll be going back to Graham's favorite hidden glue balls. And so let me call it by a G naught. We expect the mass of it to be much larger than the mass of the Higgs, given that I was talking about confinement scales for this theory of order hundreds of GeV, then the glue balls you expect them to be of order TeV or more. But this G naught can mix with the Higgs. Let me not, I refer you to this paper of Curtin and Verhaeren, where they actually discuss this in terms of the twin Higgs model. So we adopted that whole sort of methodology, but and for that reason, let's just assume an SU3, because that would be in line with the twin Higgs philosophy of having a Z2 version of the standard model. So you follow that, and you get a vacuum transition matrix element for the glue ball 0++, and you can then relate these parameters to the mass of this glue ball, which then would tell you that given the preceding definitions, this interaction would give rise to a effective Higgs glue ball mass mixing contribution, where this is given by those parameters I had in the previous plot and the scale of the EFT. Make a long story short, you get your Higgs, the mass eigenstates H and G naught, which are the propagating degrees of freedom, would become or to say differently, the gauge eigenstate particles become superpositions of the mass eigenstates G naught and H, which are the particles you would observe given by this mixing angle. And assuming that this mixing, this EFT has scales that are close to the glue ball scales, given that we are talking about TeVs, we find that this mixing is less than few percent. And if that's the case, you would expect that Higgs couplings due to this mixing would be shifted by per mil or less, which is well below current precisions for Higgs couplings, but possibly it can be probed maybe for a future in a future collider, for example, I don't know, a muon collider, 10 TeV muon collider, or 250 GeV E plus E minus, depending on which of these sort of predictions are applicable. How much time I have?
Almost no time.
Almost no time. Oh, that's so sad. So if I can have it just a few minutes, thanks. So in the twin Higgs model, you can have Higgs going to glue balls, and that gives us nice exotic signatures. This is a more hidden scenario because the Higgs cannot decay to these glue balls. They're TeV scale and Higgs is light. We can also think about the more minimal version of twin Higgs, which is the fraternal Higgs that was, among others, discussed by these people, for example. It includes the SU3X sort of hidden gauge group. So the hidden sector in these fraternal models is not a complete replica of the standard model, but it maintains enough of the features to allow for the hierarchy solution, or little hierarchy. To make a long story short, in these models, you can show that the departure, the correction to Higgs mass at two loops would come from some cutoff scale lambda squared times this is the coupling of the top, this is the QCD, and this is the mirror QCD gauge couplings. And if you assume that the hidden QCD gauge coupling is about 1.5 times the value of the QCD gauge coupling, or QCD gauge coupling, and the hidden, there would be a confinement or IR lambda pole that shows up around 250 GeV, and then you can basically convince yourself that if I set lambda squared at 5 TeV, for example, as a reasonable cutoff, you will have a 10% fine tuning. Now, Anson reminded us cool kids don't care about fine tuning, but I'm saying if that's your cup of tea, that's how much you would fine tune here. And so the essential features of twin Higgs will survive in this model, but because you don't have these Higgs decays anymore, the deviations, in our opinion, would mainly come from Higgs self-coupling deviations, and that's how you would. Okay, so let me just, in my last minute, very quickly say that I added that quartic, but I could have also added the GG dual of what I wrote down. So I can add H dagger H GG plus H dagger H GG dual. And this would have been completely sufficient to give me a potential without even the quartic. I don't even need to add the quartic. You would get this famous cosine that you may remember from Axion physics, but modulated by this confinement, or what I call instanton contribution. And then you can ask for the extrema of this function, and you would get this tangent equation. It turns out you can think about that these two clean cases, either theta, this is the theta parameter of that SUN hidden sector. If it's 0 and this is negative, this tangent, this argument has to be larger than pi over 2. But then if v squared over m squared is order 1, this is not a good EFT. So we don't really consider that as a good regime. And if it's not, one can check that the minimum viable minimum requires this theta to be very close to pi over 2, which means that there would be significant CP violation in this UV theory. And as a sample, I did pi over 2 for theta, and assuming that the scales of those two terms, the CP violent, CP conservative, are the same, and you can get a set of parameters that give you the right values. This is the funny type of the potential you would get. It's extremely flat. Of course, has tiny, tiny wiggles suppressed by this exponential, but it looks very, very flat, has the right minima, and then that's that. And you get predictions for Higgs self-coupling that are in this regime. They're small. So this would be an interesting connection between hidden CP violation and Higgs properties, for what it's worth. Anyway, I think I've run out of time, so I don't want to test the patience of my chair. So I'll leave you with the conclusions, and thank you for your attention.
Quick question. We are now time. Thank you very much. Let's thank Hooman again. Our second and third speakers have switched, so now we have Matthias.
Oh, yes, I think I'm gonna give you. You want this? Oh, do I need them?
They told me I needed it, but if you.
I think I'll try without. Okay.
Yes, so we had Matthias in the middle. So let's talk about utilizing your focus of ALPs.
Yes, thank you very much for inviting me back here. Actually, I've been here more or less continuously since the early 1990s, when Misha and friends started the continuous advances in QCD in the good old days. Now, of course, this is a new series, but it's also, I think, my second time to this one. So I'll talk about axion-like particles, and like Sven yesterday, I almost need to apologize that this will actually be about pheno and not supersymmetric instantons. And I also know that all of you are experts on axions, and even the talk by Hooman was relating to this in some extent. So, you know, I'll basically, to cut the story short, I'm going to point out that in the region where the axion-like particle has a mass that's not super tiny, that's, let's say, above the scale of the pion or so, interesting bounds can be derived from particle physics, and that actually the strongest bounds of those are the ones that have to do with flavor. So let me briefly, as a reminder, this is the Georgi-Kaplan-Randall effective Lagrangian of an ALP coupled to the standard model. And in the derivative, with derivative couplings to the fermions and the Higgs doublet and these anomalous couplings to the gauge fields, very familiar, of course. What's important is that all the couplings are non-renormalizable, so they're all naturally small, suppressed by 1 over the ALP decay constant. And also, if it was a QCD axion, the mass would also be proportional to 1 over f. So these particles are naturally light and they have naturally small couplings to the standard model. There are many subtleties related to this Lagrangian, in particular that not all of these couplings are physical. So 5 out of the 49 real couplings in these Lagrangians are redundant. This is well known. And I will always write results in terms of meaningful physical combinations of the couplings. And in particular, I will always set this coupling to the Higgs to 0, which is one of the redundancies that one has. So which flavor probes am I thinking about? Flavor changing meson decays. So in a way, the analog of things like B2S gamma, where instead of the photon, I'm emitting an axion-like particles. And the simplest decays are K to pi alp and B to K alp for the B meson. Now, of course, these will contribute only if they are kinematically allowed. So the alp mass needs to be smaller than the threshold here for these decays. So you see that this puts me in the range below half a GeV, and this puts me in the range below 4.5 GeV or so. So it doesn't go up to higher masses. And of course, the phenomenology will depend on how this guy decays. If it decays, for instance, to photons or leptons or hadrons, or maybe even invisibly to a dark sector, or maybe even it's long-lived and it doesn't decay at all in the detector. So one needs to keep this in mind, that the phenomenology here can be very rich. So in this paper with collaborators from Mainz at the time, and in fact, Marvin Schnubel is the same Marvin that was in Hooman's talk, was my PhD student some years ago. We analyzed this type of flavor constraints for a variety of decays and a variety of final states. So for instance, K to pi and an invisible alp, of course, you can get a bound here from kaon decays to neutrinos, and different final states, gamma, gamma, lepton, lepton. So those can be used to put bounds on alp couplings for alps decaying primarily to leptons or photons. And these are the corresponding bounds on the flavor changing coupling in units of 1/TeV times the square root of the branching ratio to the particular final state, which is shown here. And you see that these bounds are quite small, typically, between 10 to the 5 and 10 to the -5 and 10 to the -9 inverse TeV. And we'll come back to that a little bit later and see what that implies. There's one caveat here. In this table, it's assumed that, essentially that this decay is mediated by the flavor changing coupling of the alp, which is, of course, a possibility if there are such flavor changing couplings. But of course, an alp can also contribute to such decays through flavor conserving couplings in conjunction with the standard model we can check. So you can do the flavor change in the standard model and then couple the alp with the mesons. And that's not included here. And that's mainly what I will be discussing in the remainder of the. There's one very important feature, and this was pointed out about 5 years ago, namely the very interesting effects of renormalization group evolution. If you run a model including alp physics from the Petri-Quinn scale down to low energies. So, below the Petri-Quinn scale, you have the effective theory standard model plus alp, which is the theory I showed you before. So there's some Archie evolution here. And then at the weak scale, there are some important matching corrections. In particular, important for my talk will be that when you integrate out the top and the W, you get a flavor structure from integrating out those standard model states, which will be transmitted to the alp couplings. And then we go down to yet lower energies for the kaon decays. I will be matching that up to a chiral perturbation theory. For the D meson decay, I will evolve it down to the B meson scale and then evaluate the decay amplitude there. So kaon decay. Was a fun story when we looked at this, because this had been studied over 35 years earlier, but incorrectly. There was a missing, almost 2 orders of magnitude missing in the branching ratio due to an incorrect implementation of the chiral currents. So we corrected that and computed in this first paper, basically the leading order chi-pt contribution. And you see here what I mentioned earlier. We can, of course, have a contribution where the ALP couples directly to a kaon and a pion. So this is the flavor changing ALP coupling. But there's also contributions. G8 here stands for the weak interactions in the standard model. So you have K to pi pi, for example, and then a pi 0 mixing with an ALP, or an eta mixing with an ALP, or sort of standard model weak interactions with ALP emission and final and initial state radiation. So, you know, to get a consistent result that is independent of all the redundancies of this Lagrangian, all the diagrams need to be included. And then 2 years ago, we upgraded this calculation to the next to leading order in chiral perturbation theory. It's of course far more involved because it's a weak interaction process in chi-pt, and then in addition you have this ALP as an external source. So there's a lot of counter terms one needs in the next to leading order, weak chiral Lagrangian and QCD chiral Lagrangian, and those come along with low energy constants, which are not so well known. Some of them are reasonably well known, but some others are not so well known. So we have to do some modeling there, estimate them. There are more diagrams. All in all, it's curiously exactly 100 diagrams one needs to calculate for this decay, including the counter terms. And what we find at the end of the day is the corrections are rather uncertain because of these many new low energy constants, but they seem to be reasonably small compared to the leading order terms. So you compare the coefficients here in the leading order Lagrangian of a few terms, I didn't show all, with the next to leading corrections, you see that the uncertainties are sizable, but the sort of the mean values of the next to leading order terms are quite a bit smaller than of the leading order terms. So things seem to be reasonably under control. And now, for purposes of this table, we assume the ALP is not decaying in the detector, so it's either long-lived, which it might be if it's light enough, or decays to a dark sector. And then we can use the Na62. They've put experimental limits on K minus to pi minus plus resonance, which, you know, basically they look at the Q-square distribution of this decay. And we can use their bound to put bounds on the ALP couplings. And instead of giving you the bounds on the ALP couplings, which always come with a 1/f, which is an inverse scale, I take the inverse. So I give you bounds on f over the ALP coupling, which is a scale, which is sort of the effective new physics scale that you can poke. It's just more intuitive to us to think in terms of scales rather than inverse scales. So these effective lambda parameters for the different couplings are shown here for 2 different values of the ALP mass. And let me start from the lower half of the table. You see that, for instance, the coupling to gluons, to up quarks, to down and strange quarks, they can be probed at scales ranging from a few TeV to tens of TeV. Okay. There's a curious thing that you can also probe the vectorial fermionic couplings. Normally we think that those are unobservable, but in deep decays they become observable because the individual flavor numbers are not conserved. Like here I have a strange to down transition. So it's the difference of the vectorial couplings to strange and down actually becomes unobservable because the individual currents are not conserved, only the difference of them. And also that is constrained to about 20 TeV. And then there's the constraint on the flavor changing coupling, and all of these couplings are at the chiral symmetry breaking scale. So I think we took 1.6 GeV. And you see this flavor changing coupling is has a much, much higher bound, 3 times 10 to the 8 TeV. Okay. Now, 3 times 10 to the 8 TeV is actually a really large scale. If you would not have a flavor symmetry, if that would just be a random anarchic coupling in the Lagrangian, you know, this would correspond to an ALP decay constant. Well, it's the same number, just written in terms of GeV. I'm writing it in terms of GeV because there's this nice paper by Villadoro et al. From a couple of years ago, where they study cosmological upper bounds on the ALP decay constant. And you see that in their scenario, 30 times 10 to the 10 GeV would actually be excluded by almost 2 orders of magnitude. Now, my understanding is that these bounds have some assumptions, in particular that the Paget-Quinn symmetry breaking happens after inflation and other assumptions. But, you know, still, it's interesting that one reaches scales which are relevant for cosmology. And of course, there's an easy way to avoid this. You just impose a flavor symmetry. For instance, you say that in the UV theory, the ALP is completely flavor blind, couples to all generation in the same way. However, then these RG effects that I mentioned before come back and give an irreducible amount of flavor violation that you cannot avoid. Okay, so you have this genuine flavor violation in the high energy theory, which you can put to 0 with the symmetry, but then integrating out the standard model W and top quarks, you get the flavor change of the standard model. And when you match at the weak scale, you induce these flavor violating ALP couplings to down quarks unavoidably to the left-handed down quarks. And you can calculate this effect. And what you find is that it's proportional to VTI, VTJ. So depending on which transition here, you have certain CKM elements, some prefactor, and then the main contribution comes from the ALP top coupling. That's this diagram. You get a contribution from the ALP W coupling. That's this diagram. And at 2-loop order, you also generate a contribution proportional to the ALP gluon coupling. And the diagram is not shown here. And you know, you may think these are small coefficients. They are small coefficients, but keep in mind that we started from 10 to the 10 GeV. So we can afford to lose a couple of orders of magnitude. If you work in this scenario with a flavor universal ALP in the UV physics, these are the bounds that you get. So the coupling to gluons is probed at up to 50 TeV. The coupling to Ws is now probed. It was not probed before, of course, at the UV scale. Now, UV scale for me is 4 pi f, and f in this table is 1 TeV, but I will show you in a moment how things depend on f. You can probe the coupling to the Ws of order a few TeV, which is remarkable. You still get the strongest bound now on the top coupling, because the top loop gave the biggest flavor changing effect. And since I'm assuming the theory is flavor blind, I write CUU here because it's the same coupling for all 3 flavors basically. And you still get a 2000 TeV, which is an interesting bound, but not something that you need to worry about for cosmology. Okay, so it's safe from that point of view.
Yes, the hierarchy between CGG, CWW, CVB, which is sort of like tens and then 100, intuitively is there a simple way to the relative strength, why it decreases so much?
Well, first of all, so you know, these hierarchies are basically related to these coefficients here, but there's another contribution here from the running of these C parameters themselves. They also mix with the gluon stronger than with the W, so that's why the gluon bound becomes significant, because actually the top coupling in the low energy theory is the top coupling in the high energy theory, but then their contribution is proportional to this CGG. So one really needs to solve the RG, and it's not a simple explanation, but when you have the solution, it's clear what's happening.
But why did you choose a TeV? Because if you started higher, the running would be.
I told you that I will have a
Ah,
plot.
yeah.
TeVF for me is 4 pi f, so 12 TeV new physics scale. That's kind of motivated by hierarchy, that we maybe have new physics at the 10 TeV scale. Since these things are couplings, I mean, this is F over couplings, okay? So this ratio F over coupling, the lambdas, they only depend logarithmically on F. And in fact, if I go to higher F, I get larger running effects.
Exactly, yeah.
And you see that here the bounce gets stronger, but of course only logarithmic. Good, so, you know, these are the strongest bounce by far on ALP couplings to gluons, W bosons, and quarks. If you happen to be in the mass range below 340 MeV, where this decay can be measured. So for the remaining, whatever, 5-8 minutes or so, I'm gonna look at the corresponding B-meson decay. This is now not something that you can deal with in chiral perturbation theory, but we can go back to some very old work of mine, the QCD factorization approach for non-leptonic B decays, which basically is based on the heavy quark expansion. And I probably talked about this in one of the continuous advances of QCD meetings a long time ago. So that allows you to compute these processes. And I show you diagrams. Of course, once again, there is the flavor changing ALP coupling, in this case, B to S. And that is easy to calculate because really we just need to evaluate the B to K transition form factor. Those are computed on the lattice. And just for comparison later, this diagram scales like MB square over F. This is the amplitude for this diagram, MB square over F. And then lambda over MB to the 3/2. That's the scaling of a heavy to light transition form factor. Now, they can also be contributions of flavor conserving ALP couplings and flavor change through the weak interactions, like I discussed before for the kaon case. And this is the relevant diagrams now. And these crosses in the diagram show you where you can attach the ALP. So there's always several diagrams where you can attach the ALP. This is called the form factor contributions, because here again, the B to K form factor enters. This is called the weak annihilation contribution, where basically the weak interaction operator here destroys the B and creates the kaon. And these are called hard spectator scattering contributions. And in this QCD factorization approach, these diagrams are all calculable. And this is work with a postdoc, Upala Banerjee, and a master student, Christian Calderon, in my group at Mainz. So the question is, how large are these effects? I could show you lengthy formulas. I won't do that. I just indicate the scaling of these individual diagrams because it's interesting. That actually, it rather depends on which type of contribution you look at. So for instance, Q1 through 6 are the 4 fermion operators in the effective weak Hamiltonian. So we have these penguin type contributions where we can emit the ALP here or here or here. And this scales like, you know, the same scaling as the flavor changing ALP contribution now. However, we have a G Fermi here and 2 more powers of MB. That's the weak interaction of the standard model. We have 2 factors of CKM suppression here. Lambda is 0.2. Wolfenstein parameter. This is simply because we have BCB, BCS here, or VTB, VTS at the vertex. And then since it's a loop, a 16 pi square. So that's this contribution. We can have the annihilation diagrams. The annihilation diagrams don't have the loop suppression, but they scale, they're 1 over MB suppressed relative to this. So they have an extra factor lambda over MB. And the CKM factor here can be lambda squared over lambda to the 4th. Lambda to the 4th is if you have VUB, VUS, so that's negligible. But if it's lambda squared, these 2 terms are numerically of the same order because somehow the loop suppression is not much stronger or weaker than the power source. And then we can have this Hart spectator scattering, which are the only diagrams which allow the ALP to couple to the gluon. And actually, it turns out that if the ALP couples to the gluons, this is leading power. So again, you have the same scaling as here. And now there's two factors of alpha over pi. One is this gluon, and the other is the ALP coupling to gluons, which itself, in my normalization, goes as alpha over pi. And then for all the other diagrams where the ALP couples to the fermion lines, you get, again, the suppression lambda over m to the 5/2, but only one factor of alpha. So you see these two things are approximately equal in size, and these are also approximately equal in size. So you need to calculate them all and see what the most important contribution is. Now, I'm close to the end of the talk. Whatever I say from now on, I don't believe. But I say it nevertheless. There is a discrepancy between the measured value of B2K neutrino and the standard model prediction. It's whatever it is, 1.7 sigma, I believe. This is the measured value. That's the predicted value, 5 times 10 to the minus 6. And this is 23 times 10 to the minus 6, but with large uncertainties. So, you know, if you were to say, how about this difference is explained by ALPs, which somehow are either long-lived or decay invisibly, then those would be the couplings that you get. More likely in the future, these two values will get closer to each other, and then we could play the same game as before, that we can put exclusion limits on the couplings. But fitting is more fun, so this is what you would find. And now here the units are GeV, not TeV. And you see that the bounds are not particularly strong. The bounds on the B quark coupling is the strongest, but it's still only 30 GeV, which is not plausible as a new physics scale. The only bound that is the one on the flavor changing coupling again, which in this case is 1 times 10 to the 8, but only GeV. For the kaon case, it was 10 to the 8 TeV. So basically, we lose 3 orders of magnitude. We can still play the game of assuming flavor symmetry in the UV to suppress this strong bound. And when we do that, again, the most important constraints come on the top, the W and the gluon couplings. And this is now in TeV again. And you see that before in the kaon case, I had 1,000 TeV here as a bound. Now it's about 100. Okay, lose a factor 10. But of course, the kaons are only in the low mass range for the ALP. Now here I can go out to a few TeV. So here you see 2 GeV and 0, and you see that the bounds are almost stable. They are not strongly mass dependent. So I can go up to 4 GeV bounds. Again, these are probably too low to be realistic new physics scenarios, but this one would not be. So this would be a new physics scale at about 100 TeV with an ALP coupling to up quarks. That could in principle explain this quote unquote anomaly, but again, don't take the anomaly too seriously. This is, I forgot to put the citation. This is from this 2020 paper with Martin Bauer and Marvin Schnubel et al. And this is a compilation of flavor bounds. Everything here is flavor above about an electron volt. And you see that the kaon bounds are the strongest. And you see that the B to K bounds come in a bit more than an order of magnitude weaker, but you see nevertheless that, you know, these flavor bounds are the strongest bound in this particle physics window on these couplings. And this is the coupling to the up sector, which is the strongest. And you see B to K here. There's B to K star. And here, for instance, we assume the ALP decays to muons. Here we assume the ALP decays invisibly. So, here we assume the ALP decays to electrons, whatever data is available, you can turn this into bounds. And message here is that these flavor probes are powerful probes once you are in this window where flavor becomes relevant. This is the coupling on the gluon. You see that you lose roughly an order of magnitude, compared to the top coupling. And then this is the coupling to W, where you lose another order of magnitude. So, but again, these are the strongest. So I think I managed to finish in time. I think it's worthwhile to think about axions and axion-like particles because it's still a well-motivated class of light new physics model with naturally small couplings. So particles are naturally light, in pseudonumber Wilson bosons, and have naturally suppressed couplings to the standard model. And of course, we can use astrophysical and cosmological probes to search for these particles if they're super light and very long-lived, but if they're heavier and not so long-lived, we can also use collider probes, both direct searches like the ones I described, but also precision probes where you look for quantum contributions of the ALP, for instance, the G-2 when that was an anomaly. And I discussed the rare decays here in a bit more detail. It's simple theory, but it's kind of fun theory to actually work out these decay rates at next to leading order. And what one finds is that these are strong bounds in the range where these decays are kinematically allowed. And I mean, even though you all heard that the flavor anomalies have gone away, if you go to flavor conferences, people will still tell you that, well, the star has gone away. And there is still, depending on who you talk to, there are still tensions between 3 and 4 sigma. If you look at a bunch of observables in B2S, for example, in the B2F transition, it's still a game that is worth playing. So thank you very much.
Yes, for the future, where do you see the greatest improvement in these bounds, given that K to pi CERN is not going to, that experiment is not going to.
Yes, well, it will improve a little bit, presumably with the final release, but yeah, that's not their fault. I mean, it's really sad that the K on proton was killed, also because not as far as ALPs are concerned, but this decay K to pi neutrino is the rarest decay we have ever seen. And it's not nailed at this point, right? It's measured with a reasonable uncertainty, but whatever, 20% or maybe 30% uncertainty. And we will probably regret it if we find small effects at a certain point which would show up there. You would probably like to have a percent precision on these branching ratios, but okay, I mean, this is a done decision. So from the theory point of view, I think the B to K searches, of course, will improve. This was Bell 2, but Bell 2 really, was coming on kind of slowly because they had all kinds of issues. So these measurements will significantly improve.
So is it going to get to the level of K to pi in terms of the...
Well, it's a much larger branching fraction. I mean, it's 10 to the minus 6.
But you think the bound will get up to, you can replace...
No. I mean, no. These numbers will not change a lot because here I was taking this deviation seriously and I fitted it to the ALP couplings. But let's, if they have a value that's consistent with this one, you would basically say that the ALP effects cannot be, maybe they must be smaller by a factor 2 or so, but not much smaller. So the orders of magnitude, you can easily understand why you lose 3 orders of magnitude. I mean, it's just basically related to CKM. Because in the K on decay, it's a first order CKM suppression, and here it's a second order CKM suppression. Then you just look at the coefficients in the amplitude. It's easy to understand. Yeah, so this will not improve. This will not improve a lot, but again, this is a powerful bound, And even in a flavor universal scenario, also this is a powerful bound 100 TeV, so nicely if it still.
Just to check my understanding, so when you discuss irreducible flavor violation mediated by the weak interaction, even if you assume flavor universal coupling, there's no chance of destructive interference if you say turn on the flavor violation to work. Just checking how robust
but that would be really
conspired, but
that would be really bizarre to say I have a flavor violation in the UV,
right,
which first of all is absolutely tiny. I mean, at the level of, 10 to the -5 or 10 to the -6, and precisely aligned with the direction in which the standard model flavor points.
Yeah.
I mean, it's not logically, it's possible, but it would be super unnatural really to cancel these. And also, you get three effects from the top, from the gluon and from the W. You don't know which coupling you have and which is dominant, but
yes.
To cancel that particular linear combination of I would consider this very complex.
Yes, I agree.
You're right. Logically, you could do this fine tuning, but it would be a super fine tuning.
So this the GG dual coupling that you're working
Yes.
with should give the Axion some mass, right?
But if it was an Axion, yes. If it was an Axion, then the coupling, the CGG would, so CGG over F would essentially be 1 over the Axion decay constant, and that sets the mass. So if it was an Axion, you're absolutely right. For Axion-like particles, sort of the definition that there can be other contributions to the mass beyond that.
Yeah, but that gives you like a minimal contribution to the mass, right? So I guess I was just wondering on the parameter space plots you were showing, do you know where that line?
Not out of my head, but I can go back to the first
Yeah.
slide. So this is 10 electron volt.
I mean, if you don't
So
know.
I guess yeah, I don't know. Now one would need to look how they define the ALP blue, the ALP photon coupling exactly. There's many definitions. It's not a contradiction. I mean, you still need in order to get the mass. I mean, it could be super light. It's still relatively trying to see where we.
I guess I just wanted to know if the parameter space you were showing was below or above that line.
Oh, no, it's well, of course, I also showed you MA equals 0, which would be below, which basically just means small. And then I showed you masses of the order of GeV, and that's above what we would get.
Okay, yeah, that's right.
Let's thank our speaker. Yeah, so now we have Rachel who's going to talk to us about the standard model city violation is enough. Yes.
All right, thanks for the invitation and for the great conference. I had a really great 3 days. I didn't even notice it was Saturday when I woke up, so that's been fine. Yeah, and I'm going to tell you a little bit about a baryogenesis mechanism that does a bit of gymnastics to try and tie baryogenesis to the standard model CP violation. But I want to be clear, right off the bat, that there is definitely beyond the standard model ingredients in this model building. The point is that our CP violation comes directly from the standard model. That's the particular thing we tried to do. And this is work I did in collaboration with Gilly War, Shada Epic, and my graduate student at Florida, Martha Ulloa. Okay, so I have an obligatory dark matter and baryogenesis slide that I can sort of go through quickly for this crowd. I'm sure you're convinced that there's a mystery for what makes up dark matter, and also how even the baryonic matter that we see was generated in such an asymmetry such that it didn't just annihilate with all the antiparticles. And we got the matter that we can see with very nice pictures. So if you want to explain how the matter-antimatter asymmetry arose, you need a baryogenesis mechanism. And baryogenesis mechanisms rely on the three Sakharov conditions. One is baryon number violation. So assuming there was no initial condition for a baryon asymmetry, you need to somehow generate more baryons than antibaryons. You need to directly violate baryon numbers. You also need there to be C and CP violation, so that reactions that produce baryons are not balanced by back reactions or by reactions that just produce antibaryons. And finally, you need some out of equilibrium conditions. So even if the cross sections sort of have different probabilities of going one way or the other, if you create an excess of baryons in equilibrium, right, that's going to shift the equation, the rate of the interaction backwards the other way. So you need some out of equilibrium conditions that you can accumulate a population of one type of particle over the other type without sort of increasing through the Boltzmann equations, increasing the probability of two particles meeting and going back the other way. Sorry. Yeah, so we have at least one of these conditions in the standard model, which is CP violation. This is accomplished through the CKM matrix, which can be parameterized by the Earlskov invariant. And then when you go to low energy scale, so below confinement, one implication of the CKM matrix is neutral meson oscillation. So this reveals itself at low energies in terms of neutral meson oscillations, which is an indication of CP violation in the standard model. Sorry, I think I skipped this slide. But back in the day, people thought that if you had a first order electric phase transition, which at the time could have been possible, given the uncertainty in the measurement, like in the lack of measurement of the Higgs mass, you could have had a first order electric phase transition, and CP violation could have been generated via the CKM matrix with reactions of quarks going through or reflecting off the bubble. And there was an estimation of how much baryogenesis you could obtain from the standard model CKM matrix CP violation. And what they found by this really nice set of papers and very careful calculations, Gabela, Pilar, and friends, is that the standard model CP violation is not enough. Their answer at the end of the day was 10 orders of magnitude too small, right? So this is where the lore is the standard model CP violation. Like the standard model CP violation isn't enough, it needs some BSM effects. It came from this calculation. So I'm sorry, I did my slides out of order, I didn't realize. But what we're going to talk about is CP violation coming from neutral meson oscillations. And even though it's the same fundamental physics, it's happening at a different temperature and through a different mechanism. And so that's why this calculation doesn't necessarily directly apply to what we're doing. And so this whole mechanism was first introduced by Ann Nelson, Gilly, and Miguel. I thought this was like when I first read this paper, a really cool idea for baryogenesis, especially because when it first came out, it seemed like at the time you could accomplish this with just the standard model CP violation. And so basically what this mechanism does is it exploits the CP violation in the neutral B meson systems to accomplish baryogenesis. It also like very easily accommodates dark matter relic abundance. And finally, the nice thing about this mechanism is that it's all very low scale. And so you can rule it out with colliders. So you can access this mechanism, whereas a lot of other baryogenesis mechanisms that are perhaps more elegant are also kind of out of our experimental reach. So it might be worthwhile to like sort of look at the low hanging fruit from the point of view of an experimentalist. And so first I'm going to explain the mesogenesis mechanism in its first iteration. So how it works is there's 3 steps, and these 3 steps kind of nicely correspond to the Sakharov conditions I showed you earlier. So the first thing is that you inject B quarks at late times via maybe a decay of some long-lived scalar field, and you inject them such that they're out of equilibrium. And so that's how you get your out of equilibrium condition. If this is at low enough energies, these B quarks will immediately hadronize, some of which will form neutral B mesons. And then these B mesons will undergo CP violating oscillations. So that's how you get the condition for CP violation. And finally, what happens is the B mesons then decay into visible baryons and then some dark sector particle that carries anti-baryon number. And so in the visible sector, you get baryon number violation because you're sort of hiding anti-baryon number in the dark sector. So let's sort of look at these one by one. So the middle one, the CP violation, comes from the neutral meson oscillations. It's just an artifact of the mass states or not interaction states. So you get some oscillation in the system. And the idea is that immediately after neutral mesons are produced, or after the B quarks are produced, they hadronize and you get neutral mesons. They undergo this CP violating oscillation. And this can be parameterized by this semi-leptonic asymmetry, which is a way to parameterize what's the probability of, if you have a B bar, it mixes into a B, and then you get some final state, right, that can only talk to this B. So you started with the anti-B meson, got the B meson, you get this final state. The rate of this interaction does not equal this one, which is the other way. You start with a B, it oscillates into a B bar, and then you get the F bar state. And so if these aren't happening in an equal amount, even if you started with equal populations of these two guys, you would have unequal populations of the final state. And so this can be written in terms of the semi-leptonic asymmetry, like you can measure this at colliders, for example. You can obviously see how this is useful for baryogenesis down here schematically, and then you can get bounds on this from the colliders.
Sorry, how large is the CPV in dB bar oscillation?
So you can measure that in terms of this, and I have it on the slide. It's small. It depends on which B meson you're looking at. So it's the down and the strange type B meson. They have different numbers, actually different signs.
Or certainly larger than 10 to minus 10.
Yeah, I think it's like 10 to the minus 6, 10 to the minus
Okay,
6. There's like a window around it.
Okay.
I have it. I'm not remembering off the top of my head, but it's on a later slide. I promise. Yeah.
Okay.
Yeah. So here, maybe I'll just to answer your question rather than leave you in suspense. Sorry, it's kind of a spoiler alert. Yeah, so the standard model predicts 10 to the minus, between 10 to the minus 5, 10 to the minus 4 for the strange type. Then for the down type, between 10 to the minus 3 to the minus 4 is the standard model, and then the world averages like a bigger box. All right. Don't look too carefully at that though. It's giving things away. All right, you won't be surprised now. Okay. So finally, let's look at step 3. This is where you violate visible baryon number. Okay, so again, this is not my mechanism. This is the original mesogenesis mechanism. But still, I'm walking you through it because it like has it's this is what we played with to start with. All right, so the idea is you introduce a 4 fermion operator, and like what's going into this operator sort of depends on your UV completion, but schematically there's this 4 fermion operator that takes one standard model quark and makes 2 standard model quarks, and then this dark fermion that carries anti-baryon. And so this is how you can produce baryons. Starting with a B meson, you end up with baryons and missing energy, basically. And then the dark sector is stabilized by then doing a secondary decay. One of these guys will still carry baryon numbers. There's some like pretty constraining kinematic constraints to ensure you don't mess things up with this baryon numbers carrying dark sector. Those are my backup slides, but for time I'm going to skip over that. And then because of this, these two guys that form the dark sector, is very easy to accomplish the dark matter relic abundance. All right, so let's look at this like a bit more carefully in terms of the baryogenesis yield, right? So we want to know whether we can actually get the number we want, which is the yield of number of baryons minus number of antibaryons over the entropy. And so this B mesons to baryons plus invisibles, this is going to be limited by collider constraints. And then this guy is what's sourcing the CP violation. So we've got this semi-leptonic asymmetry here, right? And there's direct bounds on this as well as standard model predictions. And finally, like this is not, unfortunately, you don't just plug this in directly to the equation and it ends, right? You have to sort of track the Boltzmann equation evolution of these oscillations to ensure that you end up with enough CP violation to get the yield you want. And this wasn't done by us, but it was done by Miguel and this and Gilly as well. And in this, it's very carefully tracked. That gives you, and this can be wrapped up in this alpha parameter. All right, so first we'll talk about collider constraints. So like I said before, this decay proceeds through a 4-fermion operator. I gave like a particular flavor structure here, but this operator can have a lot of different flavor structures. You can put it on this bottom leg instead. You can change the final baryon that shows up. You want to start with a BD or BS though, because of the kinematic constraints in the model, so you don't mess up electron decay, etc. And so if you unwrap this 4-fermion operator, we decided we're going to pick like sort of the simplest thing, which is that you have a scalar mediator. This scalar mediator is charged under QCD, so it looks like a spork, right? So even though there's like flavor indices on all of this, which might slightly change the bounds on this decay, right? Like B mesons to invisibles and baryons of various flavors might have different bounds. One bound that's sort of a nice sort of rule of thumb bound that's going to be there for all of them is that you have to have this 4-fermion operator mediated by a colored scalar. And spork searches have been done very, very thoroughly at the LHC. And so this mediator Y has to be like, it can't, I always write this the wrong way. It can't be less than 1.2 TeV. There we go. Double negatives, the best way to present information. All right. Yeah, okay. So now the second part is this semi-electronic asymmetry and sort of tracking how efficient these neutral meson oscillations actually produce baryon number asymmetry. Like I said, this was done in this nice paper here. And I'm just going to flash the results of sort of the functional form of the alpha parameter. But it's kind of hard to get this in closed form. I mean, this is done from numerically solving like Boltzmann equations, like and also a matrix, because these are all coupling with each other. But basically what you can think very heuristically is that you want this to happen later rather than earlier, right? Because the longer these B mesons are interacting with the plasma, it's scattering off of them, which is decohering the system. So these oscillations are very consistent. These oscillations are very efficient only when they're in a coherent state, right? So you can see that like when you want these sort of to be happening sort of at late temperatures, that's when you get the largest peak in alpha, which is going to give you the highest yield. All right, so now back to my spoiler slide. So basically, at the end of the day, right, these two things are balancing each other, right? So if you have a very strong branching ratio, you can very efficiently hide anti-baryon number in the dark sector, right? And that helps increase the yield for baryogenesis. And so stronger branching ratios, which are given by these dotted lines in red on this plot. So like here's a branching ratio of 10 to the minus 4. You can go all the way up to like branching ratio of 1. Basically, that's as high as you can go. That allows for smaller and smaller semi-electronic asymmetry, right? Because these are sort of balancing each other. The more, if you have a small asymmetry, you don't get so much CP violating oscillation, but you're very efficiently transferring baryon number to the dark sector. Or the other way around, if this branching ratio is small, it's not efficiently transferring baryon number to the dark sector so well. But then you need like a much stronger asymmetry if you want to reproduce the yield that we've measured. And so, like I said, when this first paper first came out, I was thinking, wow, the standard model can explain it all. But immediately, just after these people thought about it a little more carefully, immediately you can see that this is ruled out. These high branching ratios are ruled out by collider constraints. This one shows Aleph. And this actually rules out, so if this orange box, like I said earlier, is the world averages of the measurements of these semi-electronic asymmetries in the D-type and S-type, D-type, S-type B mesons. But this is the standard model prediction here in black. And that was already ruled out by colliders, even when the first mesogenesis story showed up.
Can I ask a question here?
Yeah.
Sorry to interrupt, but I know that one always uses the semi-electronic asymmetry here, but you're not looking for a semi-electronic decay. So I wonder, we know B decays with much larger CP asymmetries, even order 1 CP asymmetries. And this is a new decay into this dark sector fermion. So couldn't you have a CP violating coupling there that gives you a much larger number here? Because the 10 to the minus 5, 10 to the minus 4, this is just the BB bar mixing, but if it interferes with the CP violation in the decay, the effects can be much bigger.
It could be, but we're actually trying to go in a different direction, which is that we want to use the standard model CP violation. But yeah, something like that could be interesting. Yeah, that's a good question, but it's kind of the opposite goal that we had. Yeah.
Okay.
So the title of my talk was "Standard Model is Enough." Yeah.
Very ignorant. What's the mass of Emilian?
5 GeV.
Yeah.
So then in your scenario or this scenario, and then you will have a modification of that. There will be quark-gluon phase of a production, but that's totally negligible, presumably, because their CPV is very small. And then we are going through the phase transition in the 5 decays to BB bar. And then you have to use this oscillation, and it decay to the psi, generating this thing.
Yes.
But I wonder if you have an actual temperature regime where this can dynamically happen. This beam edge mass is 5 GeV. By the time you finish the QCD phase transition, probably they're too heavy to have a dynamical oscillations at all. Am I missing something?
Yeah, I mean, so the idea is these are out of equilibrium, right? Yeah, so they're not being produced in the plasma. We don't want that.
Sorry.
We want them out of equilibrium. Yeah, so it's happening at very low temperatures like that. Yeah, so you're right that if this was all in equilibrium, these guys would have frozen out a long time ago. But the idea is we've produced all these C quarks.
That's right.
They're going to hadronize. They have to. Although there are some questions that have been raised about like how efficient is this process, which I don't know of anyone who's actually modeled that. But they can't just hang out. They got to hadronize, right? And so assuming they hadronize efficiently and you get from the B quarks immediately a bunch of mesons, some of which are B mesons, then this is how this proceeds. Okay, so but it's like a bit tantalizing, right? Because we're really just like, 1.5 orders of magnitude off, right? Like if we could just get around, do a little model building to get around this climate, maybe we can reopen this standard model CP violation, which to me would make the whole mesogenesis mechanism very appealing. Because I think if you're willing to go to beyond, like to add more CP spaces, etc., I start to wonder, like, is leptogenesis just a better model, right? I mean, it is a better model in my opinion, but it's hard to see. But for me, the thing that's nice about this is how predictive it is. And so like how you're not having to like put exotic sources of CP violations. So can you sort of wiggle around this a little bit and sort of maintain this predictability? And the answer that we came up with is that you can, but there's a high cost. So it's not so easy to do, even though it's tempting, right? But the answer is that it's not so easy. And then the other question, the plot from this paper, this came out after ours, but I think it's worthwhile to show because I was actually chatting with Miguel about this. So basically, so this is the same. If you look at this quadrant, it's basically the same plot, except he allowed for changing the sign of the leptonic asymmetries, sort of expanded it. And what Miguel and friends tried to do is they sort of gave up the standard model case, right? And they said, okay, instead we're going to look in this like orange region and just like use an EFT, right? And try to look at like what operators we can add that are already constrained to sort of get into this orange region and leave the standard model. And I'm like not an total expert in their paper, but I think what they ended up with at the end, they gave this, or well, I know what they ended up with at the end is this gray line, which they claim that if you use some like very modest assumptions that an EFT is sort of changing the M12, gamma12 pieces that go into this semi-leptonic asymmetry calculation from a theoretical point of view. And then you look at all various measurements from not just direct measurements of the semi-leptonic asymmetry, but also measurements of the delta M in the between the heavy and light mass eigenstates and the neutral Poisson systems, et cetera, et cetera. You actually get a much smaller gray box. And now they've sort of changed the color scheme where they put this red line not at branching ratio equal 1, but at the like thing that's not ruled out by colliders. So here's what's allowed in colliders fill the pink region. There's just this very small overlap between what's allowed and what's not, if you're willing to play those games. And so I think like the results of this paper, which I'm sorry, I miscited it. I think I cited it, somehow I've erased the citation. It was from 2024 in November or October or something. The result of this paper is that the mesogenesis mechanism in general is very much in tension. And then they tried to actually UV complete these EFTs. They found that to get to this parameter space, they have to do a lot of fine tuning. That was the conclusion of their paper. So I think this further motivates sort of, okay, can we sort of allow, can we get back to this point? Because it's not actually very easy at all to go into the yellow region and leave the standard model CP violation. So if we go to the standard model CP violation only, is this still allowed? And we managed to do it, but it's also quite hard. So this might be like sort of the end of the mesogenesis paradigm, but at least I'll tell you the cost. And if you have a better idea, I'm really happy to chat about it. Okay, so how do we revive the standard model CP violation? All right, so what we want to do is we want to reduce the branching ratio of V mesons to baryons plus invisibles from collider, and still accomplish baryogenesis in the early universe, right? And so our plan is to change the mass of the mediator, right? So we're just going to say that the mass of the mediator was lighter in the early universe, and today it's heavier in colliders, right? And so this way you lose some of the predictability of the model, but you still allow for there to be a connection between CP violation and baryogenesis and the CP violation of the standard model directly. And so what you have very schematically is this operator here gets this enhancement in the early universe relative to today by a factor of the final mass of the mediator over the initial mass of the mediator, raised to the fourth. Well, depending on what you're calculating, but raised to the fourth. And so how do we do this? So we add a morphon field that's responsible for this phase transition. And so we say that there's some new field that interacts with this mediator, and this field obtains a BEV, right? So these interactions gives a field-dependent mass to the mediator. And what we need is for the false vacuum to give the mediator a mass of 100 GeV. That's enough to get what we want. And the true vacuum has to restore the mediator mass to order TeV because the sky is a 4. So it can't be lighter than a TeV today. Unfortunately, we never discovered a bunch of color scalars at the LHC. And so if you do this, can you say that the standard model CP violation is enough? And a joke that we wrote, because I wanted our paper to say, is the standard model CP violation enough with a question mark? And then say yes, because usually question mark is no, right? Here the answer is yes. I was outvoted though, a little bit too silly for my class. Yeah, so the answer is if you do this, yes, you can get successful baryogenesis. So here's the temperature of the K, so the temperature where you put the B mesons inject them into the early universe. And what you see, and then on the y-axis here is the initial mass of the mediator, right? And then these curves are a line where you can reproduce the baryon asymmetry of the universe given some initial temperature where the B mesons show up, and then their initial mass. And you'll notice that, so first of all, like I said, these operators all have different flavor structures, so you're going to get different terms for every flavor structure, right? That's why we have multiple different lines. And you'll also notice that I flashed that plot of this parameter that tracked how coherent the oscillations were that came from the Boltzmann equation. You can see this is sort of mimicked, right? That's why I showed that plot. That's what this shape is coming from, is basically the result of that Boltzmann evolution. And so it does work. And then this is the most optimistic scenario here, where is it here? So the problem in this, one problem with this mechanism, or not problem, but annoyance, is that the semi-leptonic asymmetries have different signs in the standard model, right? And so the way we've set it up, the strange B meson system has the right sign in terms of the way we've assigned the charges of our model. We could always flip it around and give it the wrong side, and then the down type system would have the right sign, but the down type asymmetry is not as large. So we go with the strange type. And so at first we say, well, we don't know why, but the most optimistic thing is for some reason only strange type B mesons show up, right? And that gives us our most optimistic signal since there's no cancellation from the wrong sign asymmetry with the down system. And then, okay, just to give you a sense, that's the most optimistic. Maybe this is the most simple assumption, which is that we say, okay, 50-50, these B quarks half the time turn into strange type neutral B mesons, half the time turn into down type neutral B mesons. And then you get something like this. You know, this is definitely worse, but qualitatively not such a big difference. So the most optimistic thing we can get here is around like an initial mass of 500 GeV. Here, the most optimistic is about 400 GeV. So it's not like orders of magnitude difference.
So just make, so then what are the masses now? Maybe you said it
They have to be over a T.
in team.
Yeah, so maybe you can already see the problem. All right. So we need that at temperatures, at MEV temperatures, we need this thing to have a mass of hundreds of GeV, and then we need the phase shift to give them an extra, best case scenario, an extra 500 GeV of mass at these low temperatures. So this phase transition is very difficult to accomplish. Yeah, so I'm sort of giving away the next slide. But yeah, so that's why I say like it can be done, but it's like very hard. And so this is sort of like the best we could think of. So we need a phase transition that shifts the mass by about 500 GeV. This needs to happen like below QCD confinement. It needs to happen once the mesons have hydrogenized, et cetera, unless you want to play even more model building games, maybe changing the QCD confinement scale, changing the mass of the mesons. Okay, maybe that's something you want to do if you find it interesting. But in the simplest case, we just have to create this phase transition at very low temperatures. So usually this requires a high barrier between the true and false minima. And then we like say we need a few sort of basic things to get this really horrible phase transition. So we need the Y mass to shift after the baryonic symmetry is generated. So that's very low. You know, the very lowest it can happen is like BDN 5 MeV, but it has to happen below this decay temperature of where we put the B mesons, which also needs to be low, because if they hang around too long, they decohere and all this gets washed out. And then we need the universe to sort of completely exit the phase transition without messing up like BDN, it's like this. And then we want to avoid inflation. Like we don't want this field to be trapped in the false vacuum until very late times. You know, we don't want anything bad like that to happen. And so basically, generically, this requires a phase transition that's delayed to temperatures well below fine. And so we tried for a while to do like a tunneling phase transition for this. It's very hard to even find one that works that's delayed this long. And in the end, we kind of gave up and went a different direction, which is a domain wall phase transition. And we sort of sketched out this example just to say this might be one way to accomplish it. You know, usually the phase transitions that we talk about a lot are, you know, for example, the simplest is a crossover phase transition where you have some bed at high temperatures, and then it just rolls down to the low temperature bed, right? And in the case of a first order phase transition, you have some false vacuum at high temperatures, and then there's some delayed tunneling due to this barrier here, and then you fall down to the true vacuum. The domain wall formation scenario happens another way, where you have some high temperature VEV, and then you go down into two VEVs. They're degenerate enough that sort of different patches of the universe fall into one or the other. And then if these are a little bit displaced from each other, eventually the domain walls will evaporate and the whole universe will go into the true VEV. So that's the direction we went. And this can only happen if you have a very small epsilon, like less than 0.1 the quartic coupling of your scalar potential. All right. And so like I said, if the minima are degenerate enough, some patches of the universe fall into one minimum, some patches fall into the other. How much time do I have left?
1 minute.
Oh, sorry, I wasn't paying attention at all to the side. I was like, do I have 15 minutes left? I don't have that much time. All right, cool, 1 or 2 minutes. So yeah, so you guys know how domain walls work, I think, this crowd. I'm just gonna skip over this. But yeah, different patches of the universe separated by domain walls. Okay, so we want large enough patches. We need these domain walls to grow to horizon size, right? Because we want to efficiently generate baryogenesis in large patches of the universe. And so there's a few constraints on this. So we need this epsilon, which parameterizes the distance between the difference between the false and the true minimum. It's small enough that the domain walls form, also small enough that they stay around long enough to grow to horizon size, big enough that they annihilate before BBN, and then also big enough that they don't dominate the energy density of the universe. And to give you a sense of sort of the numbers that requires, you know, they're not great. So, which I mean, probably if someone's doing domain wall stuff, they're aware of. So this one's pretty mild, but in order to grow to horizon size, you need epsilon to be smaller than like 10 to the minus 6. So this is like a pretty significant source of fine tuning in this phase transition that we can use. And then once you're willing to go that small, you do have a lot of orders of magnitude to work with before you start causing problems. So here's an example of our phase transition. So here is the Morphon field values. Here's the potential of the Morphon field, and then I've also tracked the field dependent Y mass. And so in this false minimum, which it doesn't look false because my epsilon here is 10 to the minus 26. So I don't know, I don't have good enough eyesight to resolve this, but maybe some of you do. And so this is actually the false minimum. In this parameter space, we said here the initial mass is 200 GeV, so not the most optimistic scenario, just sort of a generic scenario. And then in this VEB, the mass is 1.2 TeV. And so if you're willing to accept these parameters, this works. The Y mass shifts, the domain walls are around at the temperatures we need them to be around, and they evaporate at the time we need them to evaporate. And this mesogenesis can proceed efficiently in the false stack. And then we got rid of one signal. So this whole thing was to get rid of the collider signals. We do end up with another signal, which is a gravitational wave signal from the domain wall annihilation. And this has been worked out by Galmini and friends more recently. You end up with peak frequencies for these low temperature phase transitions in the MeV region that are a good target for pulsar timing arrays. And so we did the obligatory PTA nanograph plot and showed that for some regions of our model, this can be probed. If you believe this phase transition, it can be probed at PTAs. All right, so maybe I'll just summarize that, the title is correct in that the standard model CP evaluation can be enough, but the cost is quite high, and that you have a very tricky phase transition. Basically, at the end of the day, you don't need domain walls. That's the example we gave, but you do need a phase transition that shifts a 500 GeV amount of mass at low temperatures. That's the cost. If you want a squark to be needed, which it is, something like that has to be there. And so while this avoids collider constraints, it does very generically give gravitational waves in the PTA region. Even if you were to do a tunneling phase transition, you'd end up with a similar peak frequency for the gravitational waves because that's the temperatures at which this has to happen. And further exploration could yield phase transitions that are not as bad. Maybe this tuning could be protected by symmetry and it could be technically natural. That might be a more interesting example than the one we came up with. All right, thank you.
Thanks for very interesting, although as you mentioned, seems to be a challenge to realize this. So I was wondering, I presume you want B mesons because the psi particle that comes out has to be sufficiently heavy so that proton decay is not going to come back and hurt.
Yes.
And I was thinking, would you be able to open up new parameter space if you went to charm mesons, but then raise the mass of psi, which is a much less heavy lift?
Yeah, so actually when we originated this project, that's what we wanted to do, was we wanted to morph the standard model of quark masses to allow for the other neutral meson systems to participate in the baryogenesis mechanism, so you're not just relying on the mechanism. It was very difficult to accomplish in the end because the CP violation just wasn't enough sectional sectors. They had it's this problem with conflicting signs between the various mesons, right? They just have different leptonic asymmetry signs. You can if it's the wrong side, you can rebuild your model, make the wrong side work, right? There's no wrong side. But if they have different signs and they're both there, it's a lot harder. So they tend to wash each other out more than help. Yeah, but that was kind of the original idea. And then we sort of gave up and did the morphing mediator instead. I mean, we are still sort of looking into this. It's kind of a question of how motivated we are to keep pursuing it. Miguel's paper made us a little more excited, so we were thinking, it's too hard, let's just do exotic CP violation. And then Miguel's like, you can't do exotic CP violations. And now we're like, is it worth it? Kind of on the line. Question?
아, 저, 어디 계십니까? 씨. 손이 뭐라고 하겠는데? 내가 처음 네, 감사하겠습니다. 예. 이렇게 안 하죠 원래 예 절대로. 예, 좀 볼게요 제가. 슬라이드를 좀 띄운 거예요. 예. 네, 봅시다. 잠깐만요. 예. 요 꽂아봐. 그래. 예, 될것 같아요. 너 사람? 아, 나온다. 예, 나왔습니다.
Man?
오케이.
Ah, you haven't shown.
예, 예.
Ah, good.
Or was it trying? Later for the moon after later. Okay. 그다음에 커스텀을 아무래도 뭐냐. 아, 이거는요. 이게 좀 이거 슬라이드 넘기는 거 좀 그렇게 쓰실 수 있을 것 같아요. 사람들이 그걸 안 쓰던데. 예, 사람들은 안 쓰더라고요. 근데 혹시 돼요. 이거 내가 예. 안 돼, 안 돼. 응? 따진 거? 뭐. 그게 그건지 이건 아니야 이게 아니? 아 그거 무슨 이건 이거는 이게 위에 이게 아래로 가면 넥스페이지. 뭐 가운데는 이게 정말 시야가 안 좋아.
When you get the.
It's done, right? Bongjun actually helped me, so.
Oh, your parent is. Okay. That's for your service. And sorry that you should be here over the weekend.
Something.
Oh. Yeah, I mean, since you have family, kids.
Yeah, I
어디로 가야 되는데?
오늘요?
그때지 갔는데.
오늘 sorry.
But you must be here.
I'm not
Is that workshop? Workshop set?
No, just I give a talk with him.
Oh, just today.
Oh,
Oh,
because I didn't quite.
Okay, we are your team.
And it will help it to be your strength.
Okay, thank you.
Maybe 40 minutes for Kiwoon and 20 minutes for Supergravity.
Okay.
That's
Very flattering.
You
They give me advice like I give 4 minutes to you and then 20 minutes to others. Same Choi, okay. Or reverse, right? That's not in the 20 minutes.
Okay, thanks so much. So today we're very happy to have Kim Choi to tell us something about the patch quality and scale hierarchy of extra-dimensional axis.
Okay, thank you for the introduction and also thank you very much for the invitation. Today, I'm going to talk about some size microphone. Okay. Oh, does it work? Okay. I'm going to talk about some features of the extra-dimensional action in the context of the 5-dimensional orbifold field theory, mostly about the peak equality and the scale hierarchy. So this my talk is based on mostly on this ongoing work. Oh. Nice.
Better? Okay. Ongoing work is the Yann Lee and Chang-Sub Singh. Well, as you know, the axions or axion-like particles are among the perhaps the best motivated BSM particles, which have been postulated in many good motivations, including the strong speed problem and dark matter and some others, including the axiogenesis. Axions also are ubiquitous in four-dimensional effective theory of string theory, which is perhaps the best candidate for a theory incorporating both the standard model and the quantum gravity. Well, one of the key features of the axions is that they are described by angular field variables. So that means that the axions are characterized by intrinsically a mass scale defining its field range, which is called axion decay constant. And the angular nature of the axion field implies that all axion couplings is inversely proportional to this axion decay constant f of a. That means that the f of a is the key parameter describing axion physics. Therefore, so understanding the origin of this axion scale can have many implications for the physical properties of the axion, including, of course, the cosmological features of the axion dark matters. Another key feature of the axion is that they can be naturalized because all of their couplings are constrained by the approximate global Pechain-Kin symmetry, which is non-linearly realized, at least in the low energy limit, including this constant shift of the axion field. Well, as discussed by Giovanni the day before yesterday, this PQ symmetry is often required to have a non-trivial feature called the PQ quality. For instance, for the QCD axion solving strong speed problem, it is required that PQ symmetry is broken dominantly by the QCD anomaly. More specifically, if you consider axion potential induced by the PQ breaking other than the QCD anomaly, it is required to be less than about 10 times of the axion potential induced by QCD. If you consider another type of actions, for instance, ultralight actions in this mass range, which may be, explain the dark matter, or for instance, for the case of dark energy axions, PQ breaking again should be highly suppressed to be compatible with this tiny axion mass. As mentioned, in the Giovanni's talk, in view of that quantum gravity generically break local symmetry, the appearance of such a PQ symmetry in low energy effective theory is quite puzzling. So it may require some explanations. This is the so-called PQ quality problem. Well, as for the angular axion field, we can consider two different types of actions. One I would call the field theory actions that originate from the phase of some complex scalar field. Another type of action is so-called extra dimensional actions, which is the zero mode of p-form gauge field in higher dimensional gauge theory, notably in string theory. So, typically the extra dimensional action is defined as some integral of the p-form higher dimensional p-form gauge field over some p-dimensional closed surface, p-cycle. Well, a nice feature of this extra action is that it has, at least compared to the field theory actions, they have a clear origin of the axion decay constant and qualified PQ symmetry. As for the axion scale f of a, it is apparent that the compactification of the extra dimension essentially determine this axion scale. On the other hand, it is well known that the extra dimension can provide appealing mechanism to generate scale hierarchies. For instance, the hierarchies between axion scale and Planck scale, and some hierarchies between different energy scales. The most well-known example is the large complexity volume or strong warping, and such a mechanism can be easily applied to extra dimensional actions to get the axion decay constant well below the Planck scale, as well as a large hierarchy among the axion decay constant of multiple actions. As for the origin of the PQ symmetry, you can notice that it actually arises from the p-1 form gauge symmetry associated with this p-form gauge field. For any p-form gauge field, you can consider this p-1 form gauge symmetry E1c, parameterized by the globally well-defined p-1 form gauge transformation. On the other hand, PQ symmetry is defined as a global p-form transformation generated by some harmonic one form associated with this p-cycle sigma p. So that you know that the harmonic P form is locally exact. So that means that your PQ symmetry is locally resembles the gauge symmetry, but of course not globally. So this tells that for the extra-dimensional actions, PQ breaking arise from non-local effects induced by non-derivative coupling of this P form gauge field. So you need both non-local and non-derivative coupling of CP. So then essentially there can be two ways to break PQ symmetry with this observation. The first type of PQ breaking is the PQ breaking by Chern-Simon type interactions. Typically take this from CP, obviously non-derivative interaction of CP, wedge times some closed D forms. So upon also with some integer valued coefficient, upon dimensional reductions, this Chern-Simon term generates the 4D effective coupling of this extra dimensional action to the total divergence of some current, which is not necessarily gauge invariant. Of course, that includes the well-known action coupling to the Yang-Mills instantons. Also, if your 4D effective theory involves three-form gauge field, that also describes the your action coupling to the four-form flux of your three-form gauge field. So this is the well-known PQ breaking by Yang-Mills instantons. This is the PQ breaking by the flux of this four-form three-form gauge field. Another way to break PQ symmetry is the coupling to charged P-1 brane, which is required to exist according to Weak-Gravity conjecture. Weak-Gravity conjecture tells that if we have a P-form gauge field, then there should exist the P-1 brane coupled to your P-form gauge field. So with tension bounded by some upper bound. So because this is required by the Weak-Gravity conjecture, let me call this as irreducible PQ breaking. For the PQ breaking with Chern-Simon term, somehow you can simply assume that some Chern-Simon term coupling doesn't exist, but some other Chern-Simon term exists. But for this existence charged brane, this is required by the Weak-Gravity conjecture. So this is what you cannot avoid. So the coupling of this your C-form field to the brane is described by this world volume action, including the brane tension and coupling to the P-form gauge field. Then once you have such P-1 brane, then your physical amplitude should involve the contribution from this Euclidean P-1 brane wrapping the P cycle. That's the so-called brane instantons. Then this brane instanton generates the action potential of the suppressed by the exponential of instanton action times cosine term of this action. So your instanton action is given by this, essentially proportional to the brane tension times volume of the associated P cycle. So this is the irreducible PQ breaking. So that if you wish to have some good enough PQ quality, then somehow you should suppress this strength of this irreducible PQ breaking. So if I summarize the PQ quality EDA, for the PQ breaking by Chern-Simon terms, you can simply assume that the quantized coefficient of dangerous Chern-Simon terms are zero. This is just a matter of choice, not the fine tuning. So for instance, you may assume that the coupling to the flux, giving the flux breaking, or the coupling to the hidden Yang-Mills instantons combining at high scales. Okay, you simply assume that the coefficient of Chern-Simon terms is zero. While the coefficient of necessary series terms, for instance, for the case of QCD action, you need a action coupling to the QCD anomaly, then okay, you simply assume that coefficient is non-zero. But for the irreducible PQ breaking, you cannot simply assume that the charged brane doesn't exist. On the other hand, we already learned that the resulting action potential can be exponentially suppressed, at least in the limit that the brane tension times the volume of the cycles is large enough. So this is the typical way that you get the good enough PQ quality for the extra dimensional actions. Well, many of the essential features of the generic extra dimensional action can be understood in simple 5-dimensional field models. The simplest example, to this direction might be the extra dimensional actions from 5-dimensional one-form gauge field, which is compactified on a circle. So you have a one-form gauge field. Its field strength is CMN, and according to the Weak-Gravity conjecture, then you should also have the charged matter field. So let me introduce charged scalar field here. So of course, all these field variables should obey the appropriate boundary conditions. Then this is your extra dimension actions, just the Wilson loop integral of this fifth component of the gauge field. This is your PQ symmetry transformation, one-form global transformation. Okay, if you wish to get the action coupling to the QCD, then you introduce this form of the 5-dimensional Chern-Simon term. Then again, you have irreducible PQ breaking induced by the gauge interactions of the letter. So a nice feature of this extra action from one-form gauge field in 5-dimensional model is that the irreducible action potential can be explicitly calculated with some familiar methods. The most straight way to calculate the irreducible action potential induced by the loops of induced by these charged matter fields is you calculate the theta-dependent vacuum energy density. For instance, you consider theta-dependent one-loop Cassiopeia energy induced by this gauge interactions of these charged matter fields. Alternatively, you may consider the so-called world line formulation of your 5D field theory and take the semi-classical limit. Either way, we are interested in basically in the limits that this irreducible action potential exponentially suppressed, so that we are interested in the limit that the mass of these charged matter fields is heavy enough compared to the compact physical 1 of R. So you take this limit, then you found that this form of the irreducible action potential, again, as we already anticipated, exponentially suppressed. So obviously, you see that the irreducible action potential can be minimized if you take the limit that your charged mass of the charged matter field, 5-dimensional matter fields, approach to the cutoff scale. Of course, again, this mass of these 5-dimensional charged matter fields is bounded by Weak-Gravitt conjectures, but while satisfying the Weak-Gravitt conjecture bound, you can make this m pi times R is large enough so that this irreducible action potential suppressed enough. Well, on the other hand, this 5-dimensional model on S1 is too simple, of course, to be realistic. For instance, it cannot incorporate the standard chiral standard fermions. Also, if you just stick to this model compact S1, you cannot incorporate the warped geometry for bigger scale hierarchy, for instance, which may allow this action decay constant in this range, which is particularly interesting in view of this action detect experiment and also the astrophysical implications of actions. Yet, with the relatively small modification of the model, just the jitter obifolding, we'll see that 5-dimensional model can reveal much richer features of extra-dimensional actions while incorporating the standard model successfully. Well, so let me consider simple and well-motivated examples of 5-dimensional model on this orbifold involving one-form and zero-form gauge field, giving two actions in 4-dimensional theory. Actually, this is the most general setup, at least in the context of 5-dimensional theory, for the extra-dimensional actions from p-form gauge field, because basically the one-form, if you use the magnetic description, then it's in magnetic field description, it's the two-form gauge field. For the zero form, magnetic field description, it's a theory of three-form gauge field. So that just consider one form and zero form, can cover all possibilities, including all general p-form gauge field in the 5D theory. So you have two different type actions. One, zeta C from the one-form gauge field in 5 dimension, zeta zero from zero-form gauge field in 5 dimension. Well, one specific example of this type of models involving one-form and zero-form is the 5-dimensional effective field theory of the so-called Horava-Witten heterotic M theory. Okay, thank you. In which the standard model lives on the orbifold fixed point. But here I consider the general 4-dimensional EFT, not just the low energy limit of Horava-Witten theory, but general 5-dimensional EFT in which the standard model can live either in bulk or at the orbifold fixed points. All right. Well, before moving to some details of this setup, let me first mention that the action from zero-form gauge field, 5-dimensional zero-form gauge, is not an extra-dimensional action in my own sense, at least in the context of 5D theory, because at this level, it is a local degree freedom, obviously. So its peak quality is not assured yet. So to ensure the peak quality of this zeta zero, let me make another assumption. So let me assume that my 5-dimensional theory is actually the low energy limit of the higher dimensional UV theory, involving the additional extra dimension K, including some closed surface, so that my 5-dimensional zero form is actually integral of the higher dimensional D forms, integral over some D-dimensional closed surface. Well, for instance, if I take the Horava-Witten at M theory limit, my X is the integral of the 6 forms over whole entire 6-dimensional Calabi-Yau space. This 6 form is actually magnetic dual of the 3-form gauge field in the 11-dimensional M theory. So this is my assumption. So this assumption will assure us that, okay, first of all, with the additional problem, assumption on the quantization of the charge. So this assumption actually ensures that your X 5-dimensional zero form is periodic. Okay, this is basically 5-dimensional axion, and also irreducible peak breaking for this 5-dimensional zero form induced by the charged D-1 brane coupled to XD, again exponentially suppressed, at least in the limit that the brane tension times volume of the D cycle is large enough. So this is my assumption. Okay, now, okay, this figure shows the just orbifold, G2 orbifold, just you mode the circle by the G2 reflection. All right, this is the boundary condition for the involved dynamical 5-dimensional field. Because I want to have the 4-dimensional actions from the 1 form and 0 form, so that actually fixes the orbifold boundary condition. So this, C mu should be parity odd, and while X should be parity even. As for the ion charged matter field, that this is again, required to, it's required to exist according to the unique gravity conjecture. In principle, basically, generically, we can have 2 different type of matter fields. One is its orbifold boundary condition involved the charge conjugation, so complex conjugation. While for the tilde phi, tilde matter, the orbifolding G2 orbifolding does not involve the charge conjugation. You have basically 2 different possibilities. So depending on with these different orbifold boundary conditions, we'll see that they have a different kind of gauge interactions. Okay, this is my ion gauge field associated 1-form gauge field. So let me assume that X in general can be also gauge charge. So then phi transform under this ion gauge symmetry, just take gauge transformation phi takes normal form, just described by the charge times gauge transform function lambda. On the other hand, gauge transformation of this tilde matter fields involve the epsilon function. This is the periodic step functions or domain-like. So change the sign if you move to the next fundamental domain of orbifold. And then you see that basically this continuous ion gauge symmetry is broken at the fixed point down to G2 subgroups. So for instance, if you consider the most general solution obeying this orbifold boundary condition, but just a constant, you see that this boundary condition is defined up to modulo 2 pi. So that if lambda is a constant, obeying this modulo 2 pi, then you see that the most general solution is that integer times pi. So that's the element of G2C. So under this G2C, G2 subgroup, the X is shifted by its charge times pi. Phi transform, pi and pi tilde transform like this. Well, of course, then you have a UNC gauge interactions for the charged matter fields. The main point here is that for the untilde matter fields, it takes the gauge interaction take normal form, just the constant charge times gauge field. But for the tilde matter fields and also the X fields, because of orbifold boundary conditions, its gauge interactions involve also this dit odd epsilon functions. So that this pi tilde and X has the kind of domain-like gauge interactions. All right. So this is the PQ symmetry, 2 PQ symmetries, 5-dimensional form and 4-dimensional form. So you see that as I mentioned already, for the PQ symmetry of this X field or the PQ symmetry of this zeta 0, we already noticed that there can be local breaking in principle in the context of 5 division theory, because this is the local degree of freedom in 5 division. But with my assumption on the GUV origin, the local breaking of this second, this second peak symmetry is is exponentially suppressed if I take the limit that the underlying the d-1 brane of the brane tension and the volume of the surface, this d-dimensional surface is large enough. But for the peak breaking, for the breaking of this first peak symmetry, this is the zeta C, which is extra dimensional even in the context of 5 division theory. Again, zeta 0 is not extra dimensional in the context of 5 division theory, but extra dimensional if you consider UV completions. But zeta C is, essentially extra dimensional even in the context of 5 division theory. So that means that I can calculate this irradiation potential of zeta C in the context of the 5 dimensional field theory. All right. So to examine the effect of the warping, let me consider the general linear dilaton model proposed in these works. So that basically the model involves two free parameters, K1 and K2, for instance, here also involves some dilatons. So everything is determined by two parameters, K1 and K2. So depending on their ratios, K2 over K1, for instance, if it is 0, if K2 is 0, it corresponds to RS model. If it's equals to 1, if K2 is equal to K1, it corresponds to so-called the linear dilaton model, which is the gravity dual of the so-called lead string theory. For the heterotic M theory, you find that K2 is bigger than about 6 times K1. Okay, so that this model can cover the continuous range of this K2 over K1. So for the rest of my talk, I'm going to discuss the effect of 3 features of the model: fixed point interactions, warping, and G-to gauge coupling on the peak equality and action scale hierarchy. All right. Let me first consider the additional irreducible action potential induced by the UNC breaking fixed point interaction. I already mentioned you that at the fixed point, this continuous U1 gauge symmetry is broken down to G2 subgroups. So that means that at the fixed point, you can have a whole bunch of UNC breaking interactions while preserving the just G2 subgroup. So for instance, depending upon the chart, you can have a whole bunch of UNC breaking couplings, including the tadpole terms. So for simplicity, let me consider only the scalar fields, tadpole terms, and mass mixing terms, all those kind of UNC breaking interactions. So this UNC breaking fixed point interactions provides additional source for the irreducible action potentials. So to highlight this additional action potential, let me first consider the case without any brane interactions. So if you don't have any UNC breaking fixed point interactions, then okay, you see that if you calculate the irreducible action potential, the leading contribution is coming from the loops of this pi-type fields, charged fields, circulating the covering space circle. So over one fundamental domain, you get this one phase. You get the same phase in the next fundamental domain because the charge is the constant. But for the tilde matter fields, okay, you get some phase here, but because now the charge is split the sign, so that you get opposite phase, so that the pi tilde doesn't generate any action potential, while the only pi field generates this form of the irreducible action potential, which is actually the just 1/2 of the action potential you would get in the theory of S1. So orbifold, this orbifolding make the action potential just half. But if you have a fixed point with additional UNC breaking interactions, then you get the whole bunch of additional action potential. One, presumably the dominant one, potential dominant one is this form of action potential, which arises even at true level in the 5-dimensional context. So if you have some tadpole term at the fixed point, it will generate non-zero vacuum variable scalar field localized at the fixed point. But again, in any case, if you use the some general argument, then the action potential arises always as a non-local effect. So even when you have some non-zero vacuum value of some charged matter field at one fixed point, that does not mean that your action potential generated. you need some non-local effect, some communication between two fixed points. So eventually you see that you get the experience suppressed action potential involving the the fixed point interaction at 0 and another fixed point interaction at pi. But okay, thank you. It involves propagation along the only one fundamental domain. So the suppressed not just exponential minus 2m pi r, but exponential minus m pi r. So this is presumably the most dominant addition action potential that arises from the fixed point interactions. Well, then you have a whole bunch of different type of additional potential generated by the fixed point interactions. The UNC breaking, mass terms, pi square terms, or the mixing between pi and pi tilde, so that you have this additional, action potential. So we noticed that, okay, as we already anticipate, fixed point interactions can induce a variety of additional action potential for these, extension actions that actually make a change of the detailed form of this your condition to get the good enough peak quality. But again, still, this is a non-local effect, as you already anticipate, so that it doesn't change, any qualitative change of the peak quality, although it changed some details of the required parameter conditions to get the good enough peak quality. Now, my next subject is action localization in extra dimension due to the warping and G2 couplings. All right, for this, let me consider this specific example of 5-dimensional actions. This is actually the form that I got from the heterotic M theory, 5-dimensional EFT of the heterotic M theory. Again, I have two pre-parameters K1 and K2. You know that for action decay constant, one simple way to calculate action decay constant, okay, that use this angular field basis, or theta C and theta Z angular field with 2 pi periodicity, and then calculate its kinetic term. Then the coefficient of the kinetic by definition is its action decay constant. So F scale, all of the F scale coefficient are just the action decay constant. The reason that I'm interested, again, as I mentioned, action decay constant is crucial piece of the crucial part of the action couplings. Again, so generically the action coupling written in terms of angular fields take the kinetic term, which coefficient is the action decay constant. Then action coupling to the gauge field is described by some integer valued coefficient K alpha. Still, you have the some continuous parameter C psi, which describe the action coupling to the fermion or meta fields, whatever it is. So action coupling to the gauge field for canonically normalized action field involves, of course, gauge coupling, integer valued coefficient here, and action decay constant. For the meta couplings, we have real valued continuous parameter C psi divided by action decay constant. For this integer value K alpha, they are simply determined in this 5-dimensional model by the integer valued Chern-Simon coupling in 5-dimensional theory. You can have two different type of Chern-Simon terms: 5-dimensional Chern-Simon term of 1-form gauge field C, and 4-dimensional Chern-Simon term of 0-form gauge field X. On the other hand, these two continuous parameters, f of A and C psi, they severely depend on the detailed form of the profile of your action zero mode in extra dimensions. This is a kind of well-known phenomena if you have any experience with the extra dimension models. So then we should calculate these 4-dimensional action couplings. You should calculate the first. You need to know what is the profile of your zero mode in your extra dimension. Your two actions, theta 0 and C, theta C. Well, the particularly convenient way to calculate this profile of the action zero mode is to consider how your 4-dimensional peak current round mu theta is embedded in the 5-dimensional peak current C mu 5 and D mu X. So this is one particular example. If you consider this particular limit of parameters, then you get your theta C is exponentially localized near the IR fixed point, while the profile of the theta Z is constant, even in this warped background. So that actually generates the this hierarchy between the action decay constant and Planck scale. So you get the f of C exponentially smaller suppressed, by this relative to the Planck scale, but the f of 0 is nearly saturates the weak gravity conjecture bound, just suppressed by the involved connected instanton actions. Well, there is additional localization induced by the G2 gauge interactions, parameterized by this delta M. Obviously, you see that this parameterized the effect of this Yuan's gauge interactions, G2 Yuan's gauge interactions. This additional localization also, change some detailed form of the action scale hierarchy, but its impact is not that much dramatic because the f of x is actually bounded by Euclid conjectures. That's what I'm not going to discuss not detail here. But still, this additional localization can significantly affect the action coupling to the standard model fermions, even in the limit that you don't have any warping. Well, this is scale hierarchy. Let me skip this. Let me finally mention the effect of warping on the peak quality. That how the size of the irradiation potential is affected by the warpings. Okay, for this, let me consider irradiation potential from UNC charged scalar field as an example. Okay, this is the action potential in the limits that you don't have any warping, you also no dilaton coupling, so on. But if you include the effect of warping more carefully, then actually this is the result action potential. Still take a similar form as this. Basically parameterized by the instanton action and KK scale this way. So you see that instanton action in this limit was 2m pi r. It shifted to this. And KK scale is shifted from 1 over r to this. So then immediately you find that warping can significantly improve the peak quality by first redshifting the KK scale, and also second, enlarging the instant actions. Okay, let me finish. This is the conclusion. Well, in regard to the origin of the qualified peak symmetry and action scale, which I think is two key questions on the two key theoretical questions on action physics. Extra-dimensional actions provide appealing answers. So even in the context of simple 5-dimensional EFT and compactified orbifold, you see that EDA can have a variety of different patterns of action scales and couplings to standard model, which is largely due to the action localization by warping and G2 gauge interactions. Well, finally, warping is also very useful for the peak quality in the sense that it improves the peak quality by redshifting the characteristic scale of the irradiation potential, KK scale, and also by enlarging the associated order instant actions. Okay, that's all. Thank you very much.
So I'm trying to understand how warping can improve quality. So I would naively expect that the potential generated in 5D are topological, so it's insensitive to geometry of the work, probably. Whether it is a flat versus warp, probably wouldn't know. On the other hand, warping can produce extra warping down of the decay constant compared to the overall scale. Is that how we can see that?
No. I mean, the action potential is okay. The non-locality of the action potential is topological. Yeah, right. But its strength itself is not topological. It depends on detailed geometry, underlying geometry, as you can see this, explicit calculations.
I see. So it's not that obvious how we understand. Is there one sentence way of understanding why warping can generate extra high quality compared to not warping?
I think the one obvious. Okay, it's somewhat nearly obvious that because warping can generically redshift the KK scale.
Right.
And then it's also just simple dimension analysis suggests that, okay, the characteristic size of the action potential is just the force power of the KK scale. So in that sense, if you redshift the KK scale, then it's also helpful. Not just on that, but you also find that the instant action is also enhanced. This also can be very, very important.
I see. Thanks.
But can you think of it as the profile is being suppressed on one boundary? Is that what's happening here? Because you could put arbitrary sources on PQ violating sources on the boundary.
That's true, yes.
So you should be immune to that as well.
I already used that.
Yeah, okay.
But okay, maybe you try to compare my setup with your case in previous works. So one big difference is that, my case, I'm considering some simpler setup that, I orbit only by G2. So the two fixed points, in a sense, equivalent, right? So that because of that, for instance, to generate action potential, why I need this, okay, let me go back to this, for instance, this one. Why I need both the tadpole terms at the y equals 0 and at the same time, tadpole terms in y equals pi r. So that this is a more constrained theoretical setups. But if you consider the G2 times G2 orbit folding, then you will have more general possibilities. But still, this general features that okay, U1 PQ is locally resembles the gauge symmetry. That I think always assures that your PQ breaking effect should be non-local, so exponentially suppressed. But the size, concrete size depends on the more details of the model.
You can use the holography to understand the suppression.
Sorry?
You can use the holography to understand the suppression in the sense that this axiom is composite, no?
You mean you are considering some sort of holographic duality?
Understand the suppression.
I think so. I mean, but okay. But here I consider more general warped background involving K1 and K2, right? But if I set the K2 equals 0, this RS, so then you can consider it holographic duals. Then I think much of my result can be interpreted in terms of this, CFT terminologies. I think, yes. I didn't try yet, but I will try to understand them.
As far as you go for the open folding, the charge brain induced and the borderline instantaneous decreased axiom potential, doesn't this align with the original axiom potential due to the physically confinement?
Yes, of course, yes. Yeah. Because Reheating action potential always includes the contribution from the page of the quark mathematics, so that here, no quark.
Any more questions? If not, then let's keep up.
I forgot to find this. Small pieces.
The more dangerous one is the microphones.
Oh.
No.
So it's really great to be here. I've learned a lot during this workshop. And the work I'm going to be talking about is in these two papers, and then a work to appear with my very good former graduate student, Christy Pro, who went to the postdoc in Michigan and is now enjoying Florence and Stanford. And of course, I cannot forget to acknowledge funding, the greatest funding agency in the world. So why Higgsino dark matter? And so I think to a large extent, why Higgsino dark matter is because for those of us who have thought about the traditional WIMP scenario for a long time, this is perhaps the last thing standing. But there's a good motivation for it, I think, coming from a little hierarchy problem in supersymmetry. If you just minimize the effective potential in the minimal supersymmetric standard model, and what the depot on mass squared is, it's this particular combination of the supersymmetry breaking mass squared and the supersymmetry preceding mass squared and supersymmetry breaking mass squared, plus things that are suppressed by tangent beta squared, plus things that are loop corrections. And so avoidant fine tuning suggests that the Higgsinos should be light, and so that either one of these two terms is enormously large, and so they have a chance to cancel in some natural way. Now, going along with this, the constraints on Higgsinos are relatively weak. In fact, LHC constraints on light Higgsinos, I would say, are very weak. I will say a little bit more about exactly how much very means. You can look for them through indirect detection, through annihilation to gamma rays. That's currently not constraining or not competitive with direct detection, but it has good prospects for the future. so that's exciting. And you can evade present direct detection bounds, but the theme of this talk is that, I think this is well understood, that's only true if the Higgsinos are pretty pure. And the question is, how pure is pretty pure? And so that's what I'd like to tell you about. And it's getting more and more constraining how pure the Higgsinos have to be in order to satisfy the bounds from your detection. So every talk this type has to make assumptions. Here are my assumptions. I'm assuming that our parity is indeed conserved. The lightest supersymmetric particle is Higgsiano-like dark matter. That the density of that dark matter is set by the thermal freeze-out story, even if it's less than the total density. So then the difference could be made up by axions, or insert your other favorite candidate here. Also motivated by the supersymmetric flavor problem, the problems of potential CP violation, and also the fact that the LHC hasn't seen anything yet. I'm going to assume the scalar particle of the minimal supersymmetric standard particle, the quarks, the slug size, heavier Higgs bosons are at least sufficiently heavy that they don't radically affect the dark matter story. And they don't have to be that heavy, as you'll see, compared to the other constraints that we're going to have on Higgsino. For that to be a good assumption. Okay, so for the younger people in the audience, or those who don't think about supersymmetry as a big everyday of their lives, there are 4 important parameters in this story. There's mu, already talked about, that's basically the Higgsino mass. There's M1, the Vino mass, the superpartner of the Kiwoon gate boson, the Lino mass, M2, and then very important in this story will be tangent beta, which is the ratio of the Higgs vacuum expectation values. So because we are setting limits on superpartners from the LHC, it's probably a very good assumption that we can treat everything having to do with electroweak symmetry breaking as a perturbation. So the neutralino mass matrix is, if you just diagonalize this 2x2 part, which is going to be one of these is going to be the lightest neutralino, you can treat this as a perturbation and expand in it. And I'll show you what happens when you expand in it on a future slide. And the same thing for the chargino. One of these eigenstates is going to be nearly degenerate with these. So based on my assumptions, the free-light Higgsino states have masses near the absolute value of mu, and the mass splittings are controlled by these perturbations, and that controls the purity. And so clearly, if the larger these are, when you just diagonalize the matrix, the more pure Higgsinos you'll get. Okay, so here's the well-known story about the Higgsino dark matter density. So if you compare to the Planck observation of omega h squared is about 0.12, and you look at what I've drawn here is 2 different lines. The red line is where I have relatively light Higginos. The blue line is what happens when the Higginos are pretty much heavy enough to not make a difference for this particular graph. Okay, and so if you're at about 1.1 TeV, more or less, then the Higginos will make up all of the dark matter. And if you go down to about 200, which is where the LHC limit starts to kick in, then they make up about 4%, actually a little less than 4% of the dark mass, if the mass is 200 GeV. Okay, so even though they only make up 4% of the dark matter, and so you have to multiply your cross section by basically 0.04, you would think maybe you could escape. But even for Higgsino's that light, it's extremely constraining from the xenon dark matter detectors, especially Lux Zeppelin, but also Panda X recently. And that means you can only have slight mixing with it. Okay, so before talking about that, though, let me say some words about what is the LHC saying about nearly pure Higginos. And nearly degenerate Higginos are tough for the LHC. So if you take the simplified model where they're almost perfectly pure, then there's a charge neutral Higgsino mass difference, which varies from about 250 to 355 MeV, depending where you are in this range, from 200 GeV to 1100 GeV. And so the distance traveled by the Giardino can be macroscopic, perhaps a order of millimeters or centimeters. That's one possible way you can set limits. And then you can decay by emitting a pion or soft leptons if the mass splitting is a little bit larger. That curls up in the magnetic field and is usually not detected. Although, as we will see, it's actually crucial that sometimes it can be detected. Okay, so there are 3 signals for light Higgsinos at the LHC, which I put on this plot from Atlas. I chose Atlas mostly because I like their artistic sensibilities. Okay, so if you're down here in this orange region, this region is excluded by disappearing tracks. So your charged Higgsino actually travels a macroscopic distance and then decays and disappears as a track. Okay, on the other extreme up here, you have a big enough mass splitting that you can look for soft multi-lepton bands. Okay, and in the middle, there's a relatively new technique where you actually look for the soft pion or a soft lepton, very soft lepton at slightly displaced tracks from the interaction vortex. And so actually the CMS version of this is less artistically presented, but I'll show it later, but it's a little bit stronger than this right here. Okay. You'll notice there is a little bulge here where the actual limit is weaker than the expected limit. That means they have sort of a 2 sigma excess there, and so does CMS. Okay. So notice there are no limits above 200 GeV, except maybe this one. And so now I'm going to make comments on each of these 3. The first comment is that actually in almost all of parameter space, that disappearing track search isn't actually constraining supersymmetry. So they call it the Higgsino simplified model, but as we all know, simplified supersymmetry and real supersymmetry are not the same thing. So what you can do is you can look at the pure Higgsino limit here, which I put as the dashed line, and compare to what the actual Giardino LSP mass splitting is for different ratios of the Vino to the mu parameters. And you can see that even if that ratio is 100, so if you're up here, you're talking more than 100 TeV for the Vino mass, it doesn't actually intersect this at all. Okay, and so SUSY Higgsinos are not ruled out at all by disappearing track searches unless this hierarchy is extremely large, larger than 100. The second search region I wanted to mention is this mildly displaced soft track search. Here is again the Atlas version zoomed in a little bit. And here's a more recent thing from CMS, which they notice are getting slightly stronger bands here. Okay, and so the nice thing about the CMS thing is if you superimpose this on top of that, you'll see that they've actually now closed the gap so that in all cases we get a slightly stronger limit than what you can do at left. And so this is a very welcome development. And since it's relatively young, hopefully it might even be improved and this will do better in the future. Okay, and then again for larger mass splittings, LHC searches for Giardinos and neutralinos with, and they have mild excesses, both of them, and the soft lepton channel here and here for CMS. Okay. One thing to comment about this is they make some certain fixed assumptions about what the neutral Higgsino and the charged Higgsino mass splittings are, which are not what you actually get in supersymmetric levels. So once again, simplified SUSY is not SUSY. But it's nice to see that maybe they have 2 sigma excesses in coinciding regions or at least consistent regions. But what I'm going to show you is that if Higgsino are the dark matter, you cannot live in these regions. Okay, so now moving on to the dark matter direct detection. The strongest bounds are now from the Lux Zeppelin xenon experiment. This is their limit. You probably can't read the fine print, but this is their limit as of last October on the spin independent with nucleon cross section. And here is for the spin dependent with neutron cross section. Some comments about this are, first of all, the limits are stronger than expected. I think this is sort of the fourth time in a row they've been stronger than expected, which makes you wonder if maybe they're underestimating their background or something. I'm counting in that also Panda sees a limit that's stronger than expected. It's an order of magnitude stronger than their 2022 limits based on less than a 10-year, and that was 4.2. So there are many supersymmetric dark matter models that give LSP cross sections that are above the exclusion lines. And so that's certainly a point to consider. Eventually, the experiments will hit the neutrino fog, about which I will say more in just a bit, where astrophysical neutrino backgrounds will greatly reduce the sensitivity. And so one thing I want to do is tell you about in the future, what can we expect when we reach the neutrino fog?
Sorry, when you say it's stronger than expected, based on the runtime and then the size of the experiment improved, and then you scale up based on, is that what you mean by expected?
Yeah, so they first do an expected limit and then they compute their actual limit.
Oh,
Compare the black line with the black dash line. It's lower, so.
I see.
Yeah, so.
Okay, thanks.
Okay, so for dark matter direct detection with the assumptions that I've made, the two most important couplings for the spin independent are where you exchange the 125 GeV Higgs, and for the spin dependent is where you're exchanging the zeros on mass. And so it's good to look at what those couplings look like. Of course, in our analysis, we're looking at the full expressions for them. But just to get an idea, the spin independent coupling has this form. The spin dependent has approximately this form. They have the same factor in front of them involving Higgsino masses, but they have different factors involving tangent beta and sine of mu, which is this plus minus. So some comments on this are, first of all, clearly larger Higgsino masses, because they're in the denominator, means smaller couplings and therefore weaker limits. This spin independent coupling is maximized when mu is positive, that's the plus sign, and for small tangent beta, which makes this try to cancel. Okay, and it's minimized, of course, in the opposite limit, where tangent beta is small, so you're still maximizing this, but you're taking the opposite sign. So both strong and the strongest and the weakest limits occur when tangent beta is small, and large tangent beta is somewhere in the middle. Okay, for the spin dependent, it goes to 0 when tangent beta goes to 1. Okay, but without any dependence on the sign of beta. So there's a direct detection double blind spot, meaning a blind spot in both of these for negative mu as tangent beta gets. So just to graph that, here what I've graphed is the cross section compared to its value if tangent beta is infinity as a function of tangent beta. And so the spin independent with mu greater than 0 is up here. For mu less than 0 goes down to here. It goes to it's going to its blind spot. And the spin dependent goes to the blind spot too, but not as quickly. And so if you sort of look for smaller and smaller tangent beta, eventually the spin dependent becomes the one that sets the limit as compared to the spin independent. Yes.
So when you go to the blind spot, how much would be the one loop contribution to these cross sections?
I don't think they're terribly huge.
It'll just shift the blind spot. It won't get rid of the blind spot. It'll move it to a little bit slightly one way or the other.
Right.
Here you decouple the heavy Higgs kind of.
I can couple the heavy Higgs, yeah.
And the troughs and everything. You have the couple everything.
I essentially decoupled her. I think I set things to 10 TeV. So. Okay, so what's shown here is the impact of the Lux-Zeppelin 2024 results. This is the spin independent cross section, and what I've done is I've scaled it first of all by the density. Right, so if I'm down here and the density is a small fraction, I'm taking that into account. And I'm also multiplying by this factor of 1 TeV over the mass. That just has the effect of making the graph look a little nicer because limits tend to be horizontal straight lines. Okay, and so the yellow is what's rolled out. It's about an order of magnitude farther down than it used to be. And superimposed on top of that are these blue lines, which give the prediction for various different values of the Beano mass. And so if you want to live in the white region, you can see here that for this critical value up here, you need the Beano mass to be 3.5 TeV. This is very constraining and much more constraining than it was a year ago. Okay. Even if you're down here, where the LSD mass is 200 TeV, you still need the Beano mass to be 1.4 TeV. And so if you believe in something like Higgsino mass unification, the lesson is the Gluino is way out of the picture for the LHC at least. Okay. The gray region down here is where you're going to reach the neutrino fog, about which I'll tell you a little bit more in detail very soon. Another way to show that I could have swapped you with lots of versions of that plot. That one was the larger tangent beta. So if tangent beta is small, it either goes up or down. But this is for all different values of tangent beta inside mu. What is the maximum mass splitting you can have in the Higgsino sector? And you can see it's topped out at about 7 GeV now. And that is actually set by the spin dependent. That's the red as opposed to the spin independent. And this is for the neutral Higgsino mass splitting. And that tops out below 11 GeV. So unfortunately, this is not consistent with the soft lepton axis. There's ways around that. Maybe Higgsinos aren't the dark matter because there are parity violation or something. And unfortunately, the most difficult region for the LHC is now what's favored, because if you look at a large tangent beta thing, you're talking mass splittings in the 1 to maybe 3 GeV range for most of these volumes. It's just the way it goes. Here's the projected bounds on the Higgsino mass splittings if we reach the neutrino fog. So you can see they're obviously going to be going down a little bit. Now we're topped out at 5 GeV for the charged Higgsino neutral Higgsino mass splitting, and a little over 7 GeV for the neutral Higgsino mass splitting. So again, we're going to be pushed more and more as the dark matter direct detection experiments go on into very difficult regions. These are now below 1 GeV in mass down here. Now this uses the definition of the neutrino fog given in this paper by Kiwoon and O'Hare. And one thing that confused me, at least for a little bit, is there's significant variation in this definition depending on exactly how it's implemented. So I think I'm going to skip the details of how that's determined, but just to emphasize that it depends what you're saying you're trying to do. If you're trying to discover, right? If you define a Z=5 discovery criterion for the neutrino fog, that's very sensible, but I've never seen it shown by any. What O'Hare actually did was a Z=3 discovery. I might call that excess because of the discovery. And if you see experimental papers, they actually do something a little bit different. They present a 90% confidence level exclusion. Now, discovery is harder than exclusion. So the Z=5 discovery fog cross section, where you can hope to really discover something in a relatively definitive way, is much tighter than the exclusion fog cross section. So just to illustrate that, and this graph has nothing, these plots have nothing to do with Higgsino's. This was just for WIMPs. In general, again, I've factored out the mass to make lines for limits relatively horizontal. And so LZ is here for spin independent here. This is the 5 sigma neutrino fog. We're only a factor of, what is that, about 4 from getting to there. The 3 sigma fog. Here, the blue lines are actual projections from proposed experiments for Panda XT, XLZD, and what is that, a gigaton weird XLZD. And then here, the red line is the 90% confidence level neutrino fog. But it was embarrassing, it took me an embarrassingly long time, more than 3 days, to understand why different neutrino fogs for different people were so different when they're claimed to be doing it exactly the same way. And it's because one of them was using 3 sigma access and the other is using 95% confidence level access. So you saw me. Okay, so there's lots of ways. I talked about the Higgsino mass splitting. Another thing you can do is you can say, okay, what can we try to find? An obvious thing that you could try to find is gluinos. And assuming Higgsino mass unification, now you can plot, okay, what's ruled out by LZ and what will be ruled out if we reach these various logs or these various experimental projections. And you can see, I can now make the bold prediction that in this scenario, the LHC will not discover the Higgsino. Not all that bold, maybe, and maybe it would have been bolder 30 years ago, but that's the story, right? So we're up here, we're talking, you know, tens of TeV for Higgsino masses, when tangent beta is large and mu is positive. I should say I'm plotting here sine mu over tangent beta, right? So small tangent beta positive mu is here, small tangent beta negative mu is down here, large tangent beta is in there. Okay. And so that's what it is if it's all of the dark matter. Things are maybe a little bit more hopeful if you have the Higginos down to 200 GeV, which is still possible, allowed by everything. But the lesson is the sign of mu must be negative, tangent beta must be small. Okay, so with Higginos mostly out of reach, top quarks might be a good hope for the LHC. And so you have this sort of hierarchy we look forward to, which would give you a decay that's mostly to be Higgsino, and then about a slightly smaller amount where you're going to T Higgsino. Okay, so this signal is going to look for this particular decay chain, if they both go this way, is actually similar to the bottom searches, right? And then you have things that are kind of different from, I think, what they actually looked for. And there is no LHC search that's specifically dedicated to this with a full room 2 scenario, so I can't show you that. But perhaps in addition to just assuming that you're not seeing anything from the Higgsino decays, maybe you can see the soft pions. I think that should be looked at, or the soft lepton tracks. There's only one LHC search that I could find for run 2 data that was only 36 over femtobarns, hasn't been updated. They made some sort of unfortunate assumptions in retrospect. They didn't know this at the time. But here's sort of our very rough guesstimate for what the LHC sensitivity could have been if they actually did the analysis, which I hope they will do at some point. But you can see there's room to improve and expand into this for heavier slots. Okay. Another thing you could look at, everything I showed up to there was assuming Higgsino mass unification. Of course, if the Higgsino is the lightest, it doesn't. That's the main source of the mixing. But if you have anomaly mediation, then you expect the Higgsino to be the thing that mixes mostly with the Higginos, and you could say your target is looking for those relatively light Higginos. And so here are the bounds from LZ 2024 and the future expected fog projections and experimental projections. And so you can see there's some room here to have Higginos less than the TeV. Again, the theme is mu must be negative, tangent beta must be zero. Okay, and so what you could look for is something like this, where the charge Higginos decay with sort of democratic branching ratios. The neutral Higginos, I should have said, neutral Higginos also have sort of democratic branching ratios. And again, the Atlas and CMS collaborations, I know they're busy, but I think they should prioritize searches for this. One thing that Howie has pointed out to me is that, of course, there's a same sign W signal that you can look for which they still do not have a limit. And it would be good to prioritize this since Higgsino is on the last which candidate. Okay. And so what we can add to that is if you have to choose a benchmark, I think it would be good to choose negative mu and small tangent beta. Okay, so that brings me to my outlook. So this is a highly motivated scenario still because it's largely unscathed by the LHC. There's no limits above 200 GeV at all. Some of the limits are only on simplified models that are not fairly realistic. However, where the real constraints come from are direct detection. The least constraint, as I keep arguing, is mu negative and small tangent beta. Unfortunately, you can't accommodate the LHC soft flux on mild excess, but there are caveats to this. If you add a Emilian, then direct detection, if it's the LSP, direct detection goes out the window. If you have R parity violation, that's fine too. So you should discount completely the LHC soft flux on excess. For all I know, it's already been the experimental has already killed it. I never hear any problems. There's other things you can do. There are Higgs mediated blind spots with, in my opinion, a certain amount of fine tuning. One thing I didn't emphasize is there's another blind spot you can concoct where M1 and M2 have the opposite sign from each other. This doesn't involve any heavy Higgs states coming into the interference. They can still be really heavy. But what you find out is if you tune them, if you do that tuning where you're canceling M1 and M2 contributions, then the mass splitting has to be small anyway. Okay, and I've already said that Atlas and CMS should prioritize searches for top sports in the what time do I have?
Truth, 2 minutes.
2 minutes,
Yes.
good. So when you, I understand these talks might be going on YouTube, and when you watch things on YouTube, you get advertisements. So I'm going to give you an advertisement now, which is completely unrelated. Skip button. So for the last, about 6 years ago, I started teaching the graduate quantum mechanics course. And about 2 years after starting to teach it, I decided I wasn't particularly happy with any of the textbooks out there. So I decided to write my own. And so I'm now pleased to announce I have coming out a new textbook on graduate quantum mechanics, suitable for a 1-year core course. It's going to be published next year. But until then, feel free to download it, use it, become a doctor of your course if you want to. If you know somebody else who is in that position that has the privilege of teaching this course, it's a fun course to teach. You might take a look at it. So besides the traditional topics, I cover things like entangled subsystems and open systems, generalized measurements, decoherence. And so there's my AI generated Schrodinger's cat in the form of a jaguar from an AI generated block after thinking outside the box. Thank you.
So how much does your conclusions change when you bring some particles down? So you
So not a whole lot. I think in most cases. So for example, this is what happens when you bring the top sports down. So actually you kind of, when you make the top sports sufficiently light, you sort of morph into the stop co-annihilation regions here. So there, if you make them sufficiently light, of course, you'll get deviation. I think in general, things tend to be fairly robust.
Near the end, you have a second example of Vino being the NLSP, right? In that consideration, the mixing effects start to be there for the neutralinos, right? For the yeah,
It's the NNLSP because there's the other Higgsino.
yeah, I consider Higgsino together as one LSP. Right. So the Vino will play a role also for the dark matter considerations, right? So I was confused about the benchmark choice you made here.
Right. So the logic is you cannot have the Vinos being very light because if you do, they will mix in and violate the direct detection rate. So that's why they have to be heavier than gray lines. Looking at the right thing. Yeah.
Yeah. But you still said the Higgsino mass 1.1 TeV. I thought when they are near.
So
yeah.
Right. So actually, it's not exactly 1.1 TeV. It's I choose whatever value makes omega H squared exactly 0.12.
So you actually still saturate the full dark matter for the left.
I'm sorry.
You still saturate the full dark matter radical abundance really.
Yeah. This left plot is where I'm saturating the full relative abundance. Here is where I just assume that it's 200 Higgsino is 200 TeV only because that's safely above the LHC balance curve in all cases. Yeah.
And also for this meld access, so the two experiments seem to have quite different shapes in larger splitting. One doesn't see larger splitting.
So yeah, I think the way I would say it is they overlap. but they're also not quite looking at the same thing because they're making different assumptions about the how the math hierarchies depend on their pointing parameters. So, and they're two sigma x's, right? So it's not worth. I know people have done sort of careful studies of, oh, is this left or that left? I think it's too preliminary for that, but it's fun too. It's better than having a 2 sigma jump.
So for this AMSB case, is there some viable Higgsino weak quantization region, or that all excluded?
So there can be, but I think that's probably going to be Higgsino, we know quantization. Yes,
Yeah, the mass is maybe
splitting,
higher.
and I think you're gonna, most cases, just be completely ruled out by LC.
Any more question? If not, then let's give a big pause.
So actually those different track are both studied so at 3 TV if you do the high and your process, but for sure you go down closer to
Talking, yes. Now, yes, and to change to changing slides. Yeah. I can bring mine. Yes, this one.
No. I mean, like, I need to connect this to.
Oh, yeah, so this one. Yeah. Good.
Then down, move on.
Yeah, they did that a lot. Sure, that was they studied it. Didn't remember the numbers. And this is with
Yes.
Yeah.
Thank you. Thank you for the invitation for this workshop. My title was signatures in presence of primordial black hole, but in fact I've shortened it. It was too long, so I will just concentrate on gravitational waves signatures in presence of primordial black hole instead of the reheating. Oh, okay. Down is there. No, nice animations. You see. Okay. Right. So some advertisement. Also, the second edition of my book is released. So this is even better. I mean, a lot of computation is good if you teach or if you have some lectures about early universe, and also some publicity about the students and postdoc which took part in this study. Yuanchi is there. Gunju also is there. It's not his photo here, but I could put his photo here. You will see after. And this is a list of articles, but you will find in the PDF file if you want some details. So the title of the talk, yes, is gravitational wave signatures of spectrum in the presence of inflaton and primordial black hole. So the main idea, and I will be concentrated on black hole with mass, is between 1 gram to 10 to the 8 gram, which correspond to a lifetime between 10 to minus 23 seconds and 1 second. So it is a PBH, primordial black hole, would decay before the BBM. And to see if we can have a hint of their presence by studying the gravitational wave spectrum. So, and of course, the black hole in this case can read the universe, can lead to reheating, dark matter production, biogenesis, but all the talk can be applied to any kind of early matter domination. Doesn't need to be a primordial black hole. What change is the relation between the black hole lifetime, so the parameter space change, but you can have metastable matter would decay. You will have the same kind of behavior. So that's the summary and the conclusion and the introduction of my talk. That's what I will try to explain, that the primordial gravitational wave spectrum from a frequency. So that corresponds to more or less 1 TeV. So frequency of 10 to minus 18 Hertz is there. This is the size of 10 to 42 GeV is the rate. So this corresponds to a frequency of 10 to minus 18 Hertz, so which is the size of our universe, which corresponds to the gravitational wave produced, blam, 60-fold before the end of inflation. Because of course the modes enter in the universe by expansion. So this is spectrum, so this is radiation domination, and then you have a matter domination, which will be here. You will understand why matter domination
has a spectrum which is inversely proportional to the frequency. And then at the end, you have here rho, which is 10 to minus 14, the total density. So this is the aim of the talk, is just to explain you the shape of the spectrum. Each part has different kind of physics. And I think the physics which is interesting, not so much the spectrum. I will always take 1 gram of PBH. This is what I will take, 1 gram. And I will change the mass after to see what change if I change the mass of my black hole. So this spectrum, horizontal, -1 and power, whatever, this is what we call, this is primordial gravitational waves, which were produced, in fact, during the inflation and which re-entered the universe during the reheating. And the shape depends, of course, of the content of the universe. Notice that what you read here, you really read the history of the universe, right? This is the end of inflation. You really are reading the history of the universe. If you have access to the primordial gravitational wave spectrum, we have access to the book of the history of the universe from the inflation to the matter dominations, one by one. This is really reading the history of the universe, and we all want to know what is the history of the universe. Really, the spectrum gives you exactly what happened from the inflation to now. Second part, this one, which is coming from the PBH density fluctuation. There was a talk of JC yesterday. It's the same kind of density fluctuation for matter. It is a matter density fluctuation. I will take the PBH. Can be any kind of matter. When you have a matter, you create a potential. You create a potential, you create gravitational waves. But this is matter density fluctuation, the peak you see here. This peak here, this spectrum you see here is coming from the inflaton scattering, because inflaton, of course, produce gravitational waves. You will see the relation between gravitational waves produced by scattering of the inflaton and the one produced during inflation, which are the same in the sense between Bogoliubov transformation and Feynman diagram. And of course, a peak coming from the PBH decay, because PBH, when it decays, of course, it produces graviton, it produces gravitational waves, high frequency. This is an inflation. This corresponds to 10 to 13 GeV for the temperature of the universe. This corresponds to 10 to the 10 GeV. This corresponds to 1 TeV, just to give you an idea of the temperature of the universe when these waves re-enter the horizon. And this frequency, like 10 to 15, 10 to 17 Hertz. Of course, the heavier the black hole, you will see the frequency will go toward 10 to 20 Hertz. This corresponds to the temperature of PBH. 1 gram PBH has a Hawking temperature of 10 to 13 GeV, right? 10 to 13 GeV. It's a 1 gram PBH temperature, and it is the energy more or less at the end of inflation. So 1 gram PBH is quite equivalent to an inflaton at the end of reheating. That's why you see the spectrum of inflaton is almost the same value, the same amplitude than the PBH, because 1 gram PBH is equivalent to the energy at the end of inflation. So we're reading the universe in sense from right to left, okay, from end of inflation to now, because of course the thermalization did not destroy the information that the graviton gathered all around their way. The main point of all that story of universe, we have it because graviton does not thermalize, and thanks to that, they keep in their spectrum all the information of the complete history of universe. So you really read the book of universe looking at the spectrum of graviton. And this is the only way to read it, by the way. So very, very quickly, because PBH or inflaton or production from a perturbation during inflation have the same source, is gravity. So that's why I took the two objects, inflaton and graviton, because they are source of gravity, just unavoidable in a sense. So very quickly, why you produce quanta from gravity? Okay, Einstein equation, very quick. Okay, so you understand quite well that Einstein equation give you metric is a kind of fluctuation of quanta, or fluctuation of quanta generate a metric, whatever you want to read it, which means more or less I generate fluctuation through Ricci scalar. If I have Ricci scalar, de Sitter, for instance, Ricci is a constant, is h square. So if I have a de Sitter space, I have fluctuations. If I have fluctuations, I produce particles when they re-enter the horizon. This is a short way to explain why gravity or de Sitter produce particles. Of course, same way, same. So this is for de Sitter horizon, the same for Schwarzschild radius, of course. So you have two kind of horizons, Schwarzschild or de Sitter. This is the two radius you have, which means you have two horizons, de Sitter horizon or Schwarzschild horizon. If you have an horizon, you have a temperature. If you have a temperature, you have a quanta. You can read whatever you want. You make a Bogoliubov transformation for those who are known about it, and you have a temperature, which is Hawking temperature. In the case of de Sitter Schwarzschild space, is Hawking-Gibbon temperature. In the case of de Sitter space, call it whatever you want. It is a horizon. Horizon divided by 2 pi gives you the temperature, and you have a distribution of particles, so which is m Planck square over the mass of the black hole in the case of Schwarzschild, and h lambda divided by 2 pi in the case of de Sitter space. So the vacuum, in fact, of state of a field depends on the motion of the observer. which is Unruh effect if the observer accelerates, and it is de Sitter temperature, Haugen-Gibbon temperature, it is the universe who actually accelerate, but it's the same. Acceleration means the number of particles is observer dependent. So from this temperature, you compute the number of quanta you produce. It's annually, Schrödinger already in 1939. Introduced the de Sitter space in his own equation. And notice that positive frequency becomes negative frequency and vice versa. And so notice that if you have a space which is evolving, okay, all positive frequency, if you accelerate the trail mail, some frequency become negative, and you have a creation of pair of particle antiparticle. It is Hawking evaporation, or the effect, or whatever you want, or Schrödinger effects. Is the same thing. Particles appear, antiparticle appear, and it is translated by Bogoliubov coefficients, which is the translation between the positive frequencies to the negative frequencies. Okay, because the Bunch-Davin states is not anymore a vacuum state. Okay, so Schrödinger effects, Unruh effects, Bunch-Davis for Parker works. This is a summary of the work from this from 1931 to the Parker, Zeldovich, Mochanov, of course, Ford, and Bogoliubov in 53, which is not there. So that also produces, so Schrödinger effect is the same. So you have a background field, which is electromagnetic field, and you produce pair electron positron from the fact the background field is modified. So Schrödinger effect, Unruh effect, Hawking radiation, de Sitter temperature is the same. You have a temperature which depends on magnetic field, on the acceleration of the observer, on the mass of the charged radius here, or on the de Sitter bubble rate. So whatever you have, if you have an horizon, you have a temperature. If you have a temperature, you have creation of quanta. All the rest is poetry, is computations. So this is what this method of particle gravitational production will be used in all these cases. This is the same equation in a sense, these Bogoliubov transformations, call it whatever you want, which will generate these primordial gravitational waves, whatever is the horizon. Can be a black hole horizon, can be a de Sitter horizon. So let's begin by the primordial one. This nice part of the spectrum. So this the spectrum is not so easy it's not so difficult to understand. I will make a very short way to how to compute the fluctuations from the de Sitter space. So you have a state. I will take a scalar state to simplify it, not spin 2, just scalar to understand what's happening. So you solve the equation of motion in a space which is de Sitter space. That's the equation of motion. Of course, you have the Ricci scalar which appear here, which is acceleration. This is in conformal time. And so you have a solution of this equation with the scale, which is 1 over h tau. Okay, this in conformal time, the radius is 1 over the conformal time. H is constant. And so the solution is a sum between one oscillation part and one part which is divergent, IR divergent, h over the momentum. And so when you are in the Sitter space, for the momentum which is smaller than h, so for the momentum which is go out of the horizon, you have a production of particle which is chi square, and chi square is h square. So you recover the fact that my chi square here, very easy, which is the solution. My chi square is h square over 2k cube, which means k squared d cube k give me h over 2 pi square. Cover just in one page the Hawking temperature or Hawking-Gibbon temperatures. Okay, just like this. You recover that you create, in fact, a quantum which corresponds to a distribution function of a temperature h over 2 pi. So that easy way, in the de Sitter space, of course, you have an exact solution, so it's easy in de Sitter. In our case, it's more complicated because you go from de Sitter to a radiation or matter-dominated universe, so it's more complex, but at least you know where it's coming from. And so my density of energy, my logarithmic density of energy evolution, the log, okay, you see here the log, is just k square h square. So easy to understand. So my rule is k square h square, h is fixed. It's the h of the inflation. So h is fixed. So my rho is k square h square. So my density of gravitational waves is my k square h square divided by my rho total, which is m Planck square h square, not hm square, but h square. The h square, of course, depend on when my model turn the horizon. So when k will begin to be smaller than h will catch k, and I will begin to enter on the horizon. So every time a new node is entering the horizon, and then is diluted. Right, so hn square, this is my fluctuation produced during inflation, h square, my Hawking-Gibbon temperatures, k square divided by h square. When h square is k square, the node enter on the horizon, and then you dilute like a minus 4. And of course, dilution here depends on what the universe is made for. That's why you have a spectrum, because the dilution of the gravitational waves is a minus 4. The dilution of the total depends on what the universe is made of. That's why you can see it. And so if I put some numbers, when k is equal to h, I have h divided by m Planck square, which give me 10 to the minus 14. If I take h 10 to the minus 12, h to the 12 m Planck. So 10 to the 12, 10 to the minus 20, so 10 to the 12, which means here 10 to the minus 6, 10 to the minus 12 here, I'm divided by 100, give me 10 to the minus 14. So you see that you expect any kind of density nowadays of 10 to the minus 14, the total energy density. Of course, that's why it's quite difficult to detect it. Doesn't mean it's impossible. So of course, the mode exits the horizon, I produce the fluctuations which are frozen at a given value, which is h squared. And then my horizon at the end of inflation hit again, and I oscillate again, and I see a particle. So from a frozen fluctuation begin a particle. A fluctuation which is frozen begin to become a particle because it begins to oscillate as soon as my horizon cross my modes. So what's happening? So it's very easy because now you have the evolution of h will depend on the equation of states. So once you horizon, it will be limited differently. The ratio will be different depending on what you cross. If it is radiation domination, it's easy. Radiation domination is F4. You cancel, it's constant, it's 10 to minus 14. So it doesn't change. 10 to minus 18 because you have a matter part which appears. So that's why you lost a third of magnitude compared to the one when they re-enter the horizon because you have a matter domination part after the CMB. But it's constant, of course, because it's radiation. If you are limited by matter W5 to 0, so you have something which is 1 over the frequency. It's 10 to minus 18 for a frequency of 10 to 3 Hertz, 1 kilohertz, correspond to 10 to the 10 GeV reheating temperature, so when the universe begins to be dominated by the radiation. And if you have an equation of state of 1/2, for instance, which corresponds to a potential of inflaton of 5 to the 6, you have a dependence on frequency, which is 2 divided by 5. So all is written on this equation, so it's very easy to compute. So that's why you recognize, so now nicely the spectrum. All the story is in the spectrum. Inflaton domination, matter domination, radiation domination. So all the story of the gravitational waves is imprinted in the shape of the spectrum. And you know exactly the equation of state of the spectrum by the slope of the spectrum exactly. So I really read the book of universe as I say. So the pre-BBN history. So this is this part, radiation domination, matter domination, whatever domination you have. Here it's equation of state of 1/2. Of course, if the equation of state increase, this slope will increase. And we can have access to the equation of state directly. Looking for the inflaton scattering, you also have the possibility of reduce it by inflaton story. So what is the rating? So I will skip fastly here. What's happening is you transfer the energy of the oscillation of the inflaton. So this is at the end of your rating, right? Before what already discussed, what the mode produced during inflation. This is after inflation, right? During rating, sorry, after inflation. So after inflation, the mode oscillates. If the mode oscillates, it will produce graviton. It will produce whatever, so it will also produce graviton. And the oscillation of the inflaton by solving the equation of Feynman equation gives you how many graviton you produce from the oscillation of inflaton. It's not really a scattering. Huh? It's an oscillation of inflaton. Okay, oscillation of inflaton which gives you graviton. Right, this corresponds, if you want to compare to what we did before, or the other modes, which is from Bogolyubov point of view. These modes are the modes never exit the horizon. This mode is UV mode. There's a mode where the momentum is smaller than k. So you never had this h divided by 2 pi square, right? All these modes were never frozen, so they are produced, they were oscillating in a sense, and they are produced with frequency which is at the end of inflation, they already are inside the horizon, right? They have never been frozen by the inflationary process. This, if you want to make the equivalence with what we just did before. Because what we did before, take into account. That's why the little parenthesis between the Boltzmann and Bogolyubov approach, or Boltzmann or Feynman, sometimes I say Feynman or Boltzmann, is the same kind of things. So just to give you the difference, a Bogolyubov approach, you solve an equation of motion, right? You have an equation of motion for a field. This is a scalar field, for instance. And you solve the equation and you compute the number of particles through the Bogolyubov coefficients just by solving the equation of motions. And you have a nice spectrum because, of course, you have a number of particles per momentum or per unit of volume of momentum. And you can have a complete spectrum. And the integral, of course, is h4 divided by 16 pi 4 because we know that the density at all is h divided by 2 pi. So this integral here, of course, is h4 divided by 16 pi 4. So this is Bogolyubov classical things. Now, in the Feynman approach, it's not the same because you compute the diagram with a scattering and you compute the number of states produced through scattering, right? Computing a Feynman diagram with a propagator for graviton, blah, 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 blah. And so you have an amplitude square that you compute. And in this, you observed, I go directly to the results, you have the same results. So in blue is the spectrum computed by the Feynman diagram. In red is the spectrum computed by the Bogoliubov approach. Of course, Feynman does not produce mode outside of the horizon because you cannot produce particles with energy which is not the energy of the inflaton of inflation. That's not possible by conservation of energy. But you see the shape of the spectrum is exactly the same, whatever the equation of states is at the same time, okay, it's nice because it means there is a coherence in that. But at the same time, it's strange that you recover exactly the same spectrum if you use a Feynman approach or a Bogoliubov approach, which means if you compute the mode which are inside the horizon during inflation, you have the same frequency, the same, it's coming from an annulation of frequency of the inflaton mode which is oscillating. So it's not obvious to show that it's the same swap. It is a coincidence, but it is really nice in a sense. So both approaches are the same, Bogoliubov or Feynman, you have the same number of particles at the end, so choose whatever you want. You have the same result. Now, you have a photo here. So if you compute the spectrum, it was made by Wenqi, Gonju, and Keith. When you compute the spectrum of the graviton from the scattering, this is the shape, quite complicated, so I will just keep the numbers which are interesting. For density, this is the shape of the spectrum, so depending on the equation of states, which are there on the inflaton, you don't have the same dependence of the frequency, right? This is different equation of states, okay, zero matter domination, so 0, 1/2, 1/3, so you see that the spectrum has not the same shape depending on the equation of state of the inflaton, which determines in fact the oscillatory mode after the inflation. So the PBH will play on the TRH because TRH will be given by the lifetime of the PBH. So this is where the PBH will play a role on this spectrum. It will change, in fact, the temperature of reheating, so it will change the pace of the spectrum. And this is this little bump you see here. This is cut of the spectrum here is coming from the inflaton scattering, which corresponds to energy, of course, peaked at 10 to 13 GeV. And if you redshift 10 to 13 GeV to nowadays, it corresponds to 10 to 7 Hertz. So 10 to 7 Hertz correspond to 10 to 13 GeV energy at the end of inflation. Its peak, of course, at the energy of the end of inflation. Then the PBH themselves can be source, of course, of graviton because they are themselves a source of gravity. So just to remind you what is a PBH, so they are formed if you have some overdensity above a critical density, which is around 1. And of course, when the horizon catch the overdensity, you form a PBH. So your horizon increase, PBH form a small one, and if your horizon increase, PBH larger one. So the later the horizon throughout the perturbation, the larger is the PBH mass. Right? So you create PBH when the horizon enters the perturbation. Just with some numbers. 1 gram is formed more or less at 10 to minus 38 seconds. A solar mass is formed more or less at 10 to minus 6 seconds. Just to give some numbers. And the lifetime, of course, I told you 10 to 13 GeV for 1 gram. This is the energy radiation, I mean the temperature of a PBH. So a lifetime of PBH is 10 to 17 seconds for 10 to 15 gram, which means 1 second PBH live 10 to minus 23 seconds, and 10 to 8 gram PBH live 1 second. So how you generate? So 2 ways to see gravitational waves. Of course, the decay, which is easier one, you produce graviton, so super easy. The frequency is easy, the temperature redshifted. So temperature of black hole redshifted by this ratio of temperature. The temperature of reheating is square root of the width of the black hole by mass, is rho, right? So it's easy. Rho radiation is gamma multiplied by Planck, more or less. So you put all these numbers and you see that 10 to 13 Hertz for 1 gram. PBH has a working temperature of 10 to 13 GeV, which correspond, okay, by chance, at a frequency of 10 to 13 Hertz. Right, 10 to 13 GeV is the temperature, 10 to 13 Hertz, it is nowadays the frequency after the redshift from the decay to nowadays. That's why it's high frequency, higher frequency than the frequency of the inflaton. That's why the peak is on the right. So you have a spectrum. When you redshift is a black hole spectrum. I mean, gray, we call it gray, not black hole spectrum, it's not gray body, is not black body, is gray body spectrum, because it's not exactly black body spectrum. So, but nowadays, the same shape of spectrum more or less, just redshifted by the fact you have an expansion. And this is what you see. Of course, we use code, black hole software, etc., because you have to take into account the fact the black hole does not decay in exactly at what time. You have to take into account the possibility of reabsorption of what is decaying. So that's why the spectrum is not like a peak. It's a little bit transformed by the fact you have gray body factors. But this is more or less what we expect, 10 to 13 Hertz. Perfect. Second generation of gravitational waves, more or less what JC discussed last time on the talk. It is from density fluctuations. So PBH, of course, has some density fluctuations. They are like a gas of matter. Okay, imagine PBH like a gas of matter. And of course, they will generate potential. So density fluctuation of delta rho will generate, of course, the potential fluctuation, scalar fluctuation. So isocurvature to curvature fluctuations. So by the Poisson equation. So I can compute my potential from my density perturbation. I have a potential and I have a spectrum of potentials from my density perturbation. And of course, from my metric, I can generate at second order my gravitational waves. And the source of my gravitational waves is my potential, which is itself created by my density perturbation. Density perturbation, scalar perturbations, and gravitational waves at second order. And it is what we call a transfer function. We compute it. So you have to compute transfer function from delta rho to Hig. A little bit tedious calculation, but what's happening is exactly that. So easy to understand what is the spectrum. The minimum wavelength, of course, is the distance because between PBH. You have PBH who are moving, they create wave. So the minimum is the distance between the two PBH. And of course, the maximum is the size of the horizon, which is causally connect. So you know which shape of the spectrum is reading by the distance between two PBH to the size of the horizon when they decay. That's exactly the spectrum we expect. And that, as you see, so the decay. And when the PBH decay, you should see the spectrum between the violet and the orange, which is very easy to compute. Distance between two PBH is the MBH divided by the density, is 1 over the density, more or less. So it's MBH is more or less MBH cube on M Planck 6. Very easy to compute. Is the distance between two PBH is known, and the size of the is the lifetime of PBH, okay, which is MBH cube over M Planck 4. So we have the life of the PBH, and we have the distance between two PBH, and this will give me these two frequencies you can observe in the spectrum. So the peak is coming from the distance between two PBH, which give you more or less 10 to 6 Hertz for 1 gram. And the lifetime and the size of horizon is more or less 10 to the 3 Hertz for 1 gram. So the spectrum of this kind of density fluctuation is between kilohertz to megahertz. This is what we expect for PBH. If you change the mass, you see it's some power, but the shape will not change a lot. So the sharp spectrum, you notice this is a sharp spectrum, because of course, once PBH decay, there is no any more gravitational wave produced by the density because there is no density fluctuation. So this is the lifetime of PBH. This is the reheating. That's why you see that you recognize that it fits exactly, of course, when the PBH decay, and this is the matter domination of the PBH. Okay, so all is fitting very well. The power of K, and you have a little change of power when PBH dominates here, from K to 11/3. So this is little computation, is all the team of Domenech, Sasaki, Vena, Langlois, etc. So a lot of teamwork on this density fluctuation. It's hard to explain just like this in 1 minute, this power, but you can. So if I change the mass of PBH, that's what will happen, okay? For 1 gram to 10 to the 8 gram, the spectrum does not change a lot. Of course, if I increase the mass of my PBH, my redshift is smaller because it decays later. So I have higher frequency because my PBH will decay later if it is heavier. So my redshift is smaller, so I will have higher frequency. And on the opposite, if my black hole is heavier, my density, my phase of matter domination will be small. And so we have less and less phase of density domination of PBH. This is easy to understand also. Yeah, perfect. 5 years is perfect. Just a little subtleties, which is what we call the burden effect. So burden effect is an effect coming from the infinite theory of information. So which say that in a system of high storage capacity, the information stored in the system tends to react to resist the process of information lost. What it means, if I have a system that loses information, okay, when the amount of information is equivalent to the amount of information which stay in the system, there is a tendency to resist to the loss of information. So it corresponds to half. It's not clear to what it corresponds, but more or less, when you lose information and what you have lost is the same amount that what you have in your system, the system does not want anymore to give information. And it can be seen as a back reaction in a sense, which that is usually parameterized by 1 over the entropy, which means the more entropy you produce, the more difficult it is to give information to the system around you, you need to keep it. So if you translate it in the PBH, of course, it's exactly the same. When the PBH decay, the semi-classical black hole lifetime has to be reduced by an entropy when the mass of the black hole is half of its original mass. So you parameterize by L1 over Sn. Of course, nobody knows exactly what is this function. It can be any kind of function of the entropy. but let's say the power of entropy is a more natural one, easier one at the end, and this gives me a different lifetime for the PBH. So you have a PBH will decay, it should have decay here, but when the half for the mass is obtained, it does not need to decay anymore. The lifetime is reduced by the entropy factor, which render it longer. So if you apply it to the gravitational waves, this is the new gravitational waves taking into account the burdening effect. Of course, you have two peaks. You see very well the two peaks because you have the first decay and the second decay. The second decay is a little bit after, so that's why the peak is a higher frequency because it redshift more. And I put here the spectrum without burden effect in gray. So you see exactly what's happening. It's almost equivalent to increasing the mass of PBH. A little bit different because two peak, but you see that you go to the right here because you have less black hole dominations. That's why this peak go to the left and this peak go to the right because you decay later, so you have less redshift. Here, less time to dominate. Here, less redshift. So on the right and on the left. So that's I think the end, just a little possibility also. It is a Bremsstrahlung we took into account. You can have Bremsstrahlung of graviton if you produce a right-handed neutrino, for instance, which is very heavy because you couple with steam in you. And so you have a spectrum of graviton Bremsstrahlung. Black hole can decay into right-handed neutrino, which give you a graviton as a Bremsstrahlung, or inflaton scattering can also produce a graviton from the product of the scattering. So that's the spectrum we obtain. So at the end, if I make the summary of possibility detection, you can ask to Sebastian. Okay, he will answer to you how you to detect this kind of spectrum. So this is a summary. Our spectrum, you have gravitational spectrum, you have the density perturbations, inflaton scattering, you have the PBH decay, and you can add on the top these Bremsstrahlung, which are around here. Oops, Bremsstrahlung is around here. So this is a complete spectrum, at least. I mean, not complete. You can always try to find other sources, but of preliminary gravitational waves. That's where the experiments are nowadays, and that's at the end the main point we have, which is the complete preliminary gravitational wave spectrum. Thank you very much. Tony.
Yeah, so people also were talking about this memory effect where the black hole, is that the same?
Yeah, this is memory effect.
Ah, I see.
We call it burden. Burden effect is memory effect. It's burden memory effect. This is exactly that. Yeah, yeah.
And this causes the black holes to be more stable and to be done.
Yeah, because it resists. It resists. So it's coming at the origin of value of 2012, 2011 of memory.
So this is Diwali.
Yes, they applied it last year. In fact, it's a theory information paper. They applied it to a black hole just last year.
I see.
And this year they changed a little bit, telling this transition is not sharp, it's smooth. I think 1 month ago, they made a paper taking a smooth, not boom, but a smooth transition between the two states.
I see.
So there was a lot of discussion about the memory. I don't say I believe in that. I just say it is not completely crazy. Some people say it's crazy. No, the fact of having a lifetime which is sharp, t minus t cubed, is a semi-classical approach a little bit strange. So the fact of telling is you smooth it. I don't know how to smooth it. I agree 1/s something. Okay, this I agree. It's phenomenal. The fact that the more you produce, what you produce on you for making you, I can buy this one.
I see. Yeah.
This I can buy it. Yeah. And so with this kind, lifetime of course of pH is much longer. That's why you can now have PBH dark matter.
Exactly.
10 to the 8 gram.
Exactly.
Because they live more than 10 to 17 seconds. That's the point. Yeah.
Questions? Not then. That's good.
Thank you.
Nice. 99 degrees.
Of course, if you clear the whole particular one is better than both.
Yeah, good stuff.
Yeah, 7.
Thank for that.
Well, that wasn't wrong.
And you can see it.
That's sort of basically an accident.
Like I said, it's
I have to somewhat impressive.
Right.
that
It was sensitive.
seems to show there's a final side of it.
Small enough to still not.
Or resonance system isn't possible.
I think the reason is that everywhere else we go. Here it's just like.
Started writing it.
Yeah.
I don't know. Let's ask Tony. Tony is the local man.
Use it.
I wanted to make sure.
Maybe
They're caring for it. Soft pilots. Very challenging things for observers. And when I think about future, we say, oh, in the future, maybe we can. Always upgrade, but.
Yeah, I'm not thorough. The point graded would be.
There's another track.
Fun. It's like almost dead.
See the Genesis?
Yeah.
I think it's must be dead, unless someone has a better idea.
Oh, yeah, you have to shift the pendulum. Oh.
So much,
Oh.
such a.
Again, I mean, it's a valiant attempt that almost works, like with prep. I mean, okay, it works with certain parameters.
Yeah, it works if you're willing to fine tune it, and I didn't highlight it, but it's bad fine tuning.
No, I could tell that, yeah.
Yeah, it's not natural at all. But yeah, so like, every loop makes it worse. So, yeah, it's cool.
Hi, Natsumi.
Hi.
I'm Wenjin.
Yann mentioned you like this.
I heard that you. You were here like 10 years ago.
Like it's 8 years ago.
No.
Yeah, yeah.
Did you overlap with Kunio?
No, actually, but I don't know. I'm working on.
I worked with Kunio when I started there.
I see.
Maybe Kunio just
I
when
see, I see.
started. Yeah.
Yeah, it's nice to see you. Yeah, I recognize you because many people.
Yeah, one was now as well.
Yeah.
Thanks. How did you like Minnesota? Where was that?
I mean, I like beer here. Local beer here. And also I could write a lot of paper with people here. So yeah, I enjoyed it pretty much. Although I mean I don't really like winter time.
That's commonly.
Sure. Yeah.
Yeah. Oh, Japanese people. Yeah.
Oh, really?
Yeah, your hair was. He was.
You
Yeah, we overlapped. Yeah, your whole 1 year, and we were in the same office.
I see.
Yeah.
Oh. That's great.
Yeah.
So I will be here until next Friday. Yeah.
You'll be. Oh, you're staying for a week.
Yeah.
Oh, nice.
So
nice.
yes, if we have a chance.
Yeah, sure.
let's discuss.
Here. It's nice to have people still staying in.
Yeah.
Beyond workshop.
Yeah.
Great.
Do you think Yann is still remaining here? I mean, Yann Mambrini? He's going to left.
Yeah, he's leaving
He's
this
leaving.
weekend.
I see.
On the tomorrow.
Over just behind the chair. Oh.
Hey. I wonder how many people are leaving. Did you see that?
People have left.
Yeah, I suspect.
Good.
Me too. We can take him out of the big bag.
No, it's different. My place was different. I mean, the campus is different. I'm in the main campus.
Okay.
Yeah, center of Tokyo.
Which one is for me?
Okay.
It's not better than
I really appreciate it.
Oh, no, really so good.
Are they coming now or?
No, after.
I've never been to Higgsino.
I went to the last Cosmos.
In Kyoto.
It's in Kyoto, but before I did tourism in Kyoto.
I see.
Tokyo is it's like nice.
How about Kyoto?
Kyoto is also nice, but it's I have like a city record. Kyoto is last year. And Paris is last year. And Kyoto, I think Kyoto plus Osaka is last year.
Okay.
Yeah. In itself, it's nice. So yeah, sometimes you get bored. Stay too long.
Especially these days, there are a lot of tourists in Kyoto.
Yes.
Yeah.
But there's also.
Yeah, it can be very hot.
You can also just stay.
Yeah.
Okay.
You don't need to show you, I can show you, because
David
David E. using it yesterday. I'll show you. I mean, of course, I can take you over there, but it'll be the same. Is that what you want?
So-
Or do you wanna?
People are more interested in that.
See,
I can let you into the building.
Oh, I know. But
That's he was there 8 years ago.
8 years ago. Eight
Here.
Yeah, 8 years. Oh.
Here.
So you're the last speaker?
No,
Or second to last?
Second last.
I remember when I was here in 2012, I think I was the last or second to last.
Oh,
I
really?
remember like, oh man, like just between the lunch or the last coffee break and then
I
that
see.
shit, like half the audience disappeared, like, oh. So this time I was like, I will stay for the whole thing, because I remember what that felt like.
Okay.
Well, and the flight was not till 7.
Or
Who knows?
11, you haven't
Yeah.
checked,
I checked
and it's the last time.
constantly. Well, they won't change it till like 2
Oh.
hours. Okay, well, still on.
Sometimes they will let you know. I mean, it doesn't help because it's not, if they say, it's 2 hours late now, they could move it back.
They can undelay it.
They can undelay it.
I think can undelay it.
They'll send me a text message that says your flight is less delayed.
Well, because they're waiting for the okay to let,
Mm.
they don't leave because they know they can't land.
Mm.
So they have to wait until they get clearance to land.
Yeah, but that can make people miss the thing. Delay that.
Yeah.
Well, yeah, I mean, otherwise you have to just go and wait at the airport.
They don't care about your time, yeah.
Well, they said it probably do, it's not the airline, there's nothing they can do, and then they just can't leave.
But Murphy's Law says that they'll only message me that there's a delay after I've gotten into the taxi.
Oh, yeah.
A third of the way through.
Or they'll text you when you're in the security line.
Yeah.
So it happened, I don't know, it was within the last year, I had a flight and they texted me, actually, I got it before.
While you were still home?
And so, yeah, while I was still home, so, okay, fine, all right, so I just waited an hour. They got into the Uber, and then as soon as the Uber pulled away, I got another hour delay.
Yep. It's that same pesky Murphy's Law in action.
Well, this is just, I mean, at least you were able to wait it out.
Oh, right.
But if you've been checking luggage, often they still have the same deadline as checking luggage,
Oh.
regardless of it.
Oh.
So you still have to tell them, yeah, just.
Oh, yeah.
I should never.
But you don't have to-
Flying off?
No. Leave it.
And I'm Spanish.
For Spanish, especially, sorry.
Especially.
You know, Italian, you have some.
In the case you can say that.
Spanish, I do.
But come on, you live in California.
Yeah, that's.
You have no excuse, Yuri.
You're right.
All right, well, let's get started with the afternoon final session. And our first speaker in the session is Natsumi Nagata from University of Tokyo. And he's going to tell us about the neutron star limit on the Axion.
Thank you for the introduction. Thank you, well, here until the very last session. So, yeah, actually, I was here 8 years ago, so I'm very happy to be here again. So I'd like to make the organizer to invite this workshop. And I changed my job title because I thought, especially young people are more interested in access that could be like good talk about. But anyway, so yeah, I like this. And I have been working on this kind of stuff for maybe 6-7 years. And recently I had some updates, so that's why I did this. Okay. Thank you. Oh.
Does it working? Okay. Okay, let me start. So let me start with some historical notes. So I will talk about this Cassiopeia A neutron star. So this is related to Cassiopeia A star. So in 1680, John Flamsteed, who was the first astronomer royal, recorded this star called 3 Cassiopeia on this date. But weird thing is that no one has observed this star since then. But now we think we know why. So this is because most likely this was the supernova. So actually Chandra found took this kind of picture, and they could identify the supernova remnant. And also they found a neutron star in the center of this supernova remnant. So this is a neutron star which I will consider during this talk. And from the motion of the supernova remnant, they could estimate the explosion date of this supernova. And this was something like this. So this is consistent with this state, by the way. And the reason why I would like to focus on this neutron star is that this has a very interesting observations. So, so these people found that from the Chandra data, they found a decrease in the surface temperature of that neutron star. So this is the only observation so far for isolated neutron star. So, and as I will talk about, this kind of observation can give you a limit on the presence of extra cooling sources like Axion. But anyway, so they found about 3 to 4% decrease in 10 years. So this data is something I'd like to discuss during this talk. Okay, so this is today's topic. So first of all, I'd like to discuss that this cooling data can be explained within the standard neutron star cooling scenario. And this is a little bit tricky, so I'd like to explain a little bit in detail. So we need actually neutron superfluidity to explain this cooling data within the standard neutron star cooling scenario. And another thing I'd like to explain is that if you include the Axion, then actually that contribution may spoil the successful explanation of the Cassiopeia neutron star cooling. So this gives you a limit on the Axion. So this was our previous work. And if time allowed, I also want to discuss recent update on the limit of this Axion. Okay, so let me start with the standard neutron star cooling scenario and how to explain that data. So just for simplicity, we consider a neutron star composed of neutrons, protons, and leptons. So leptons means electron and muon. But actually, for our discussion, the composition itself doesn't so much is not so much important. So this simple setup is fine. But important thing is that people expect that both neutron and protons in neutron star form Cooper pairs. And this is important in a discussion. But anyway, once you have this kind of setup, you can solve the so-called TVO equation of motion, and you can construct neutron star. And all the particles here are supposed to be in the beta equilibrium, and especially in the Fermi degenerate states. And once you have this system, the temperature evolution of this system can be controlled by this equation. And this is kind of very simple. So this is the heat capacity and temperature, core temperature. And these two denote the cooling sources, cooling luminosity in this system. So there are two cooling sources. One is a photon from the surface of neutron star, and the others are coming from neutrinos emitted from the core. And photon emission is just given by the usual Stefan Boltzmann law. And other neutrino emissions are more complicated. And actually, for young neutron star, this emission is found to be dominant. And especially in my talk, this process becomes important. So I will talk a little bit more about this process. But anyway, these Ulka processes and the Bremsstrahlung processes are kind of, I mean, it's easy to understand. This is just a inverse decay, beta decay and the inverse beta decay, basically. And this corresponds to the, so this is accompanied with the momentum exchange with other nucleons. And this is just a Bremsstrahlung. So maybe you can easily imagine for these three processes. So I'd like to explain this a little bit more. So this is associated with the formation of Cooper pairs. So as I said, actually, both protons and the neutrons inside the neutron stars are expected to form Cooper pairs. And when these Cooper pairs are formed, I mean, around the critical temperature, it can emit the gap, the energy corresponding to the gap energy through neutrinos, something like this. So this contribute to the cooling rate. So this is the so-called PBF process.
So Natsumi, these Cooper pairs, or what's the attraction there? Because normally
These are just a nuclear interaction.
yes, it's not a phonon based, lattice based at all. Inside the
No.
neutron star.
So
It's just some attractive force.
yeah,
That's it.
yeah. So probably as you imagine, this introduces uncertainty. For example, the size of the gap for nucleons, like neutrons, important parameters in our analysis, but there is an uncertainty in the calculation. There are some calculations, but still there is a huge uncertainty.
But mechanism is some Coulombic leftover residual force from the strong interactions, basically.
Yeah, something like that. Yeah. Here, actually, I intended to show the calculation for the pairing gap. So, for example, before going that, I would like to mention that there are three possibilities for the Cooper pairs inside the neutron star. And so neutron in the crust can form the singlet Cooper pairs, and neutrons in the core are supposed to form the triplet Cooper pairs. And proton in the core are supposed to form the singlet pairs. So this is just basically determined by the density of this one. So here I show the size of the gap for proton singlet and neutron triplet, the functions of the Fermi momentum, I mean density. So as you can see, so these are corresponding to other models. So there are a lot of models proposed. But as you can see, there is an uncertainty. But all of these show the, order of magnitude similar size for the critical temperature or gap size for proton singlet pairing. So for neutron triplet, it's more, uncertain, even more uncertain. There is a order of magnitude difference. But anyway, this is the current situation. So I will treat this as completely unknown parameter in the following discussion. And I will choose one of the model for proton singlet pairing gap. But anyway, so here I choose one particular set of the pairing gaps for neutron and proton respectively, and show the typical behavior of the cooling luminosity for each process, like a photon emission, a modified Luca process, a Bremsstrahlung, and this is a PBF emission. And you can see this peak here around this time. So this corresponds to the time of the critical temperature for the neutrons in the core. So that's why if the core temperature becomes close to the critical temperature, it suddenly enhances the neutrino emission. So this is a property we are going to use to explain the Cassiopeia neutron star cooling data. Okay, so this is the idea given by these people to explain the Cassiopeia neutron star cooling data. So basically, they just changed the size of the critical temperature from this value to 0, because this is almost unknown. So then they try to fix this temperature to explain the cooling data of the Cassiopeia neutron star. And they succeeded. So they claim that if you take the critical temperature to be this value, you can explain the Cassiopeia neutron star cooling data. So this is proposed right after this data was observed.
Yes. Is the data, does the data correspond as a flat part, or does it overlap with this critical temperature?
So this one is the data, these are the data.
Yeah.
And critical temperature is a little bit higher than this. So it's not so good to show this plot maybe, because this is corresponding to the surface temperature. And this one is relevant for core temperature. So actually, so there's a one-to-one correspondence between core temperature and surface temperature. And as far as I remember, I think the formation occurs around here or something like that, a little bit before this observation time. Okay, so actually they are more optimistic about this. So this paper is actually this paper, and there is another group which where they also claim almost the same thing, and they regard this as a first evidence for the presence of superfluidity in the neutron star core. So maybe since these two papers becomes a little bit famous, maybe some of you know this claim. But anyway, this was the logic. They think there is a superfluidity inside a neutron star.
So just to make sure, we actually don't know what's the phase of matter inside a neutron star here, right? So this work is really just to say, I want to explain what's the temperature energy loss rate that I observe.
Yeah.
I postulate there are some phase transition happen, and I just use that energy loss.
Yeah, yeah.
There's no evidence from other.
So yeah, I don't want to say this is the evidence, but yeah, this is what they say. Oh. Yes, I agree.
Create another energy loss mechanism, and also
Yeah.
can explain that.
Of course, yes. So I feel it's too much. Anyway, you're right. Okay, so what we'd like to do is something like this. So we just talked about the standard neutron star cooling scenario, but if you additionally include the cooling source, actually the cooling can become something like this. So overall temperature, of course, decreases. And also, since the cooling rate is also a function of the temperature, if you decrease the temperature, cooling rate also decreases. So then, in this case, you are not able to explain this data. So by using this fact, we try to derive a limit on the extra cooling source. And we discuss Axion as a cooling source of this. So I'd like to show the result first. So just to remind you, Axion has a coupling to nucleons, I mean protons and the neutrons. And there are some model dependencies. But important point here is that for the case with the Axion, actually the coupling with neutron is quite suppressed. So they basically couple only to protons. So this, because of this reason, actually we obtain a weaker band for case with the model because it doesn't couple to neutron. So I will show you later. So before our work, actually, this guy tried to use this new cooling source to explain this data. And he claimed that actually we can explain this data by using the emission of axions. And if the axion has a coupling to neutron with this size, then you are able to fit the data. So this was the point discussed in this paper. But we found that actually he neglected the axion proton coupling completely. But in the realistic model like this, we also expect the coupling with protons. So we decided to include this and try to see what happens. And first of all, I'd like to show the typical behavior of the luminosity of each process. So axion is emitted through the PBF process, similarly to neutrino, and also Bremsstrahlung. And this red line corresponding to the PBF process of proton and neutrons, respectively. And these are Bremsstrahlung processes. And this black line corresponds to the neutrino emission. And as you can see around the time here, actually axion emission can be as strong as neutrino emission. So we expect that this gives some effect at least. By the way, here we took the axion decay constant onto this value, which is kind of border of the limit coming from the supernova. And actually, I took KSBZ model, and as I discussed, actually, this one doesn't couple. I mean, the coupling of this one with neutron is so suppressed, but since this has a coupling with proton, actually the axion emission rate is sizable. Then we try to use this observation to set the limit on the axion decay constant. So this shows the fit. We try to explain the Cassiopeia and neutron star data. So if there is no axion, we can explain this, something like this, by choosing critical temperature in a proper manner. But if you include the axion and makes the coupling larger and larger, finally, we fail to explain this. So by using this, we can set the limit for something like this, for KSBZ and DFSD respectively. And this one found to be comparable to the usual supernova axion limit. So this was found, we found some time ago.
Sorry, is the sort of concordance of those two limits a coincidence, or does it actually make sense because it's the similar processes that's leading to cooling in both?
You mean this one, or this one, and this one?
Yeah, the latter. Yeah.
It's a little bit difficult question because I mean, in one sense, both are coming from the. I mean, both are related to the neutrino emission. I mean, the emission from neutron star, but I would say the processes we consider is quite different. So, yeah, I'm not sure whether this is totally correlated with each other. But roughly speaking, both of these, I mean, result by comparing the emission rate of neutrino and axion. So in this sense, there are some relevance, I guess, but I don't know.
So if you remove the PBF assumption, what would your result be?
It should be much weaker. So yeah, so even if I remove this one, we still have this one is just a Bremsstrahlung.
Right.
So this should
There's
be
a coupling by a lot.
Yeah, so this is just factor 5 or something. So maybe axion decay constant, a limit on axion decay constant will be a factor of 3 or something weaker.
Wait. Sorry, another question. So didn't you just say that PBF has a big uncertainty on it, big theoretical uncertainty?
Yeah,
or something? So how did you account for that in setting the limit?
So actually, so there are two important pairings. So one is for proton and one is for neutron. And for neutron, we just fix the value. I mean, we just assume the particular shape, like something like this, with the height fixed to this, in order to explain this cooling curve. Yeah, we a little bit play around with this value, but the resultant limit doesn't change so much. And for this proton singlet, actually, we took this one. So this is kind of a largest pairing gap among this set of this. And this is needed because, so I didn't really explain, but the presence of gap has another role. This suppresses the neutrino emission, actually. So in order to consider the most conservative limit, we took the largest gap. But of course, now we are working on the uncertainty coming from the choice of these pairing gaps and equation of state. So I hope we can publish a result, including this kind of discussion. Yes, thank you for the questions. And okay, so now I'd like to discuss the update from the first paper. So actually, this guy, so this is the same guy as in this paper. We visited the same Cassiopeia neutron star cooling band or cooling data, and now he also included the axion proton interactions, and probably he agrees that we can just use this to set a limit. So there is no, I mean, we cannot explain this by choosing this. But actually, his result is a little bit different from ours. So for DFSG case, his result is completely consistent with ours, but he obtained a way weaker limit for case BZ. So this introduces another question. So we looked at the source of the deviation, and it seems that according to their plot, actually this PBF emission of axion from proton looks quite different from our result. So maybe we thought that probably this the deviation between these two originate from this proton PBF. So we wanted to check what happened here. So first of all, we visited the calculation of the emissivity by using the so-called Bogoliubov transformation method. So we use this calculation for our previous work, and this one is based on the some use of transportation equation, and also they looked at the correlation function of nucleon axial current, and then obtained the emissivity formula. And we thought probably this method is more accessible for our field. So we just revisited the calculation, and actually we obtained the result same as this one. So this was the first thing we checked. And then I like to compare our result with Leinson's result. But unfortunately, he didn't provide any derivation of the Axion emissivity. But we found that there are some semi-analytic formula provided in the paper, but unfortunately, this result changes over the archived version. But we just look at this one, and we found that actually this showed a different dependence on the effective mass. So effective mass is effective mass inside the neutron star, and actually this can be very important because so in this figure, I show the ratio of the effective mass against the vacuum mass for proton and neutrons as a functions of the radius inside the neutron star. And these different colors correspond to the different choice of equation of states. And of course, there is a huge uncertainty, but still, you can see that actually this ratio can be as small as 0.5 or something like that. So if there is a difference in this factor, it can lead to the 1 order of magnitude difference. So we looked at the difference. So actually, there is another paper which also shows a semi-analytic formula for the axion emissivity. So I just compare our result, which is denoted by this black line, with the papers which we found. And this one is the Leinson's result. And this blue one is from this one. And actually, they considered some medium effect, the modification, the correction on the axion emissivity from the medium effect. And we also checked consider two cases, with and without medium effect. But anyway, our result agrees well with this blue result, but this agrees with this one. So yeah, I hope we are correct. and our previous limit is correct, still correct. So finally, yeah, last 5 minutes, right? So I will just briefly mention the observation and update. So there are some discussion even on the observational side, because so for a long time, the cooling data was obtained only from the data taken by this graded mode of the detector. And this paper suspects there is a kind of instrumental effect, and this causes the apparent cooling data. Then these guys try to use another mode on the same detectors, and then actually they also found the cooling. And by using all the data obtained so far, this paper, we revisited the cooling data and found currently find a 2.2 plus minus 0.3 decrease in 10 years. So this is the current situation. Of course, they are going to take other data. So yeah, in the future, maybe we can be more certain on the cooling in the neutron star. So anyway, this is the current status. So we have more points than I showed before. So hopefully soon, we would like to show you the updated Hasse neutron star limit on the Axion. Okay, so that's all. Thank you very much.
That's Natsumi. Do we have any further questions? Keep.
So for the equation of state, there's lots of uncertainty.
Yeah.
And so, I mean, you talked about, you know, the proton content, but what about hyperon content and all of that? Does that go into all the different curves that you're?
So yeah, as you know, of course, there are huge uncertainty from the choice of equation state. And even though you don't consider the presence of hyperon, still there is a huge effect. And if you consider the hyperon, actually, usually you cannot explain the neutron star temperature data because there is another cooling processes. So it is known that actually the presence of hyperon is not so good for neutron star for two reasons. One is it's hard to explain the equation of state which is compatible with the observed radius mass relations. So this is one thing. And cooling also doesn't work with the hyperon data. So usually people do not take into account the possibilities of hyperon, actually. But even if you forget about the uncertainty coming from the presence of hyperon, actually there is a huge kind of huge uncertainty. So for example, here I show the equation of state dependence of axion emissivity as a function of radius. And as you can see, so we use this one. And in the new calculation, we use this one. But anyway, so as you can easily see, there's a huge uncertainty. So now we are taking into account this uncertainty and look at what's going on for the limit.
Any questions?
So then discrepancy with the other author, it's fully solved, or
I mean,
or one case you're saying it's still.
So actually, I talked about this with the author of this paper, and yeah, for this result, actually, they think it's our result is correct, but I didn't send any message to this. So for the moment, I don't know. But actually, as far as I know, I don't see any paper, another paper he disagrees with that result.
Okay, there's no further questions. Let's thank Natsumi again. Okay, our next speaker is Emilian Dudas from École Polytechnique in France, and he's going to tell us about a unique coupling of the massive spin two field to supergravity.
So first of all, thank you for the nice invitation to be here for this workshop. And my talk will be pretty much formal, so very different compared to the rest of the talk. So please relax. It's also the last talk of the conference, so just enjoy the time spent here. So that's work done in collaboration with a colleague from École Polytechnique, Yann, and my PhD student, Gabriele Casagrande, and Adrien Lauti, who is a joint student with Guillaume. Everybody is from École Polytechnique. So, what is the story? The story is the following. So, the story is to try to consider, in addition to the usual graviton, a massive graviton. So, that's one of the theory which would be called big gravity theory. And you probably know that you have one massive spin 2, let's say massive graviton, or our graviton plus an additional massive spin 2, only these theories have a cutoff, which is below the Planck mass, in between the mass of this massive spin 2 and the Planck mass. So these are effective theories. The cutoff can be raised if you have a Kaluza line, for example, compactification 5 to 4 dimension. The cutoff goes to the Planck mass. Of course, you have a spin 2 states in string theory, but this comes with an infinite set of massive spin 2 fields, infinite set of higher spin 2 fields, not necessarily spin 2, but higher. And in this case, the cutoff will go to the string scale. And our goal is the following, is to take massive spin 2, put it in a supersymmetric multiplet, which is contains in addition to the massive spin 2, two massive spins 3/2, if you want, gravitinos, if you want, but they are massive, yes, and a massive spin 1. So this I will call it massive spin 2 multiplet. And we'll try to couple this to supergravity, to the massless, if you want, standard supergravity in flat state. And try to see what's happening in this case. Now, usually when you take theory, when you embed the supergravity, you solve problems. For example, Karim told you yesterday that until the emergence of supergravity, people believed that there is a problem with the Lagrangians for Rita-Ginger spin 3/2 fields, especially if they are charged under an additional U1 gauge symmetry. And these problems do not arise in the usual supergravity, standard supergravity if you want, or gauge supergravities if you have charged gravitinos. So this supergravity solves these problems. Now, in this case, you'll find something which looks a bit strange, as we will discuss, that if you take a massive spin 2 field and you couple it in the simplest possible way to supergravity, you will find something a bit which superficially looks different, and we'll try to interpret this. And then, so our goal is to construct such a Lagrangian. That's what we did, strictly speaking. And then we try to interpret is it related to a Kaluza-Klein theory in which you truncate somehow to one mode, or is it more related to a massive 2 field in a string theory? And then until which energy scale such a theory is valid. This is the goal of what we did. So we take this massive spin 2 multiplet that I'll try to introduce, couple it to supergravity, and maybe the interesting result technically is that we find the unique result. We don't have any free parameters under the simplest assumptions that I'll tell you. We find the unique Lagrangian. And so first of all, I'll go to the construction, which if you want is a so-called Noether kind of construction. In other words, the graviton coupled to energy momentum tensor, the gravitino couples to supercurrent, supercurrent energy momentum tensor go into a multiplet which was constructed in the rigid supersymmetry case by Ferrara-Zunino. This multiplet is called the multiplet of currents. This was extended to other formulations by other people, and this was the way that people computed supergravity Lagrangians by supersymmetrizing such couplings. So that's what we'll do. So I'll spend a little bit of time on this supercurrent superfield, and then I'll give you the result without going into details. And I'll show you that maybe strangely enough, the Lagrangian we have contains 4 derivative terms. So contains higher derivative coupling, which comes from supersymmetrizing in the simplest way the coupling of this massive spin 2 to supergravity. And I try to argue that what we find is not related to the usual Kaluza-Klein reduction, but is more taking a massive spin 2 from a string theory, taking it out from the spectrum, and coupling to supergravity. That's what we find. And this seems to be the straightforward supersymmetrization of this coupling. Then I'll discuss about unitarity in cutoff, and if I have time, relation, but it's not very important to Kaluza-Klein theory. So what is this spin 2 multiplet? So as I said, this is not really a phenomenological talk. I just have one phenomenological comment at the very end, but it will be cheap. So this is the multiplet, a massive spin 2, 2 spins 3 halves, and 1 spin 1, all of them the same mass. And the supersymmetry transformations can be understood in various ways. And the simplest way to understand the supersymmetry transformation is the following. You take the Lagrangians of Pauli fields, if you want. So this is the Pauli fields Lagrangian for massive spin 2. You add the corresponding one for the spin 1. It's a kind of a Proca Lagrangian, if you want. The similar one for these 2 spin halves. And if you want to make them supersymmetric, you find these transformations that you see here. That's one way to see these supersymmetry transformations. The other way is to start with the supersymmetry 5 dimensions. You do Kaluza-Klein reduction of these 5-dimensional transformations. You pick up one mode only, you truncate the rest, and you find the same. So there are very different ways to understand these supersymmetry transformations. Now, the way to couple to supergravity, and that's called the Noether method, is the following. So that's the supergravity multiplet, n equal 1, the simplest n equal 1 supersymmetry, supergravity, coupled to these massive fields. You take the energy momentum tensor of this massive multiplet, you couple it to the metric. You take this supercurrent coupled to the gravitino. And to do this, you need the so-called superfield, supercurrent superfield, which was constructed, first of all, in rigid supersymmetry by Ferrara-Zunino, then was extended in a way which was very useful to some formulation of supergravity by Sonius-West, and it was generalized in various contexts by Komarkovsky-Seiberg more recently. So this is a superfield. Doesn't matter details. Its technical term is called a linear multiplet, but it doesn't matter much. It's a superfield which contains as components U1, a current, the supercurrent, the energy momentum tensor, and something which will be auxiliary fields, if you want, in the language of superspace. So this is the current which will couple, if you want, to supergravity fields. So here you see the graviton coupled to energy momentum tensor. You see the gravitino coupled to the supercurrent of this massive multiplet. And then there is auxiliary field supergravity coupled to this current here. And then you can have something else depending on which auxiliary fields you are using here. And the most important supercurrent multiplet that is for us is this one here. So forget the rest. This is something which contains an R current. So this is an R current. It's a current of an R symmetry that I'll specify. Supercurrent, energy momentum tensor, and this is an auxiliary field. It's an auxiliary field, which, and this was used to construct the so-called new minimal off-shell formulation supergravity, which appeared later on after the original one, which is called old minimal. So the logic is the following. We start, so the logic is the following. You start with constructing the R symmetry current by using an obvious R symmetry. So this is the R symmetry acting on the two spin-3/2 states in multiple fields like this and acting on the supersymmetry parameter in this way. You construct the corresponding current, and then by performing supersymmetry transformations, these supersymmetry transformations can be understood in various ways. In particular, they are related to the supersymmetry transformation of the supergravity fields, but they can also be worked in by themselves, as Ferrara-Zumino did in the original paper. If you take the supersymmetry transformation of this R symmetry current, you find the super current. If you take the supersymmetry transformation of super current, you find the energy momentum tensor. That's the logic. You start from this R symmetry current, which is an obvious object you construct by the usual Noether formula. By supersymmetry transformation, you find the supercurrent energy momentum tensor. That's roughly the logic.
Why you started with the R symmetry?
Because in our case, in this, because this the Lagrangian that you will see has automatically this R symmetry. It has this R symmetry, so that's a simple way to find this current here, because you know the transform, you know that there is an R symmetry, you know the charges, you write right away is this current, and then by supersymmetry transformation, you find this and this.
But do it the other way.
We could not do it in the other way, but it's probably possible, but we didn't. We did it like that. Yeah, it should be in principle possible. All the formulations are not always completely equivalent to each other. Formulations for gravity. This is the logical way in this case. Now, when you do this, what you find is the following. You find in the energy momentum tensor is the trivial one. The trivial one is what? You take the Pauli-Fiat Lagrangian, you compute the energy momentum tensor by Noether method. You take the Procca Lagrangian, you compute the energy momentum tensor. You take the spin 3/2 Rita Zinger, like you compute the energy momentum tensor. That's what I call this T min UK. That's the simplest one, the kinetical, if you want, one. And then you find that your result contains something more. This something more in the language of quantum field theory are called improvements to the energy momentum tensor. These are terms which, you know, these were introduced a long time ago, before all these stories by Callan, Coleman, and Jakiv, in which they say you can modify energy momentum tensor by adding terms which do not modify the charges. They don't modify the conserved charges, but they modify, for example, the trace of the object, for example. And you find that in this case, indeed, the energy momentum tensor contains more terms. And you are imposing the condition that this term should be diffeomorphismally variant. Just from the, I mean, this is 4 dimensions. What I'm doing is 4 dimensions. I'll comment about Karuta time, but it's surely 4 dimensions. And then you realize that the 2 terms we have here, one of them is diffeomorphismally variant, I write explicit, and the other one is not diffeomorphismally variant. And then the logic is the following: you have to do something. So this theory is not diffeomorphismally variant. So what we did is to improve the whole supercurrent, the whole multiple of supercurrents, to add an improvement to this. In other words, to change, if you want, the even the R symmetry current. For the time being, we didn't write a Lagrangian. We are just playing with this multiple of currents. We are modifying this. We are improving the whole multiple of currents in a certain way, such that the energy momentum tensor we find correspond to a diff invariant theory. And there is, I spare the details. There is we find just one way to do it, is to change this R current by adding this term here. So these are the 2 spin 3/2 fields. If you are changing we are adding this, which is an improvement, does not change the conservation. You see it immediately, it does not change the conservation because these indices are antisymmetric. If you take a derivative here, this does not give, doesn't change the conservation. It also does not change the charge. Then you find an energy momentum tensor which has an improvement, which in the Lagrangian formulation correspond to a term in this contains a lot of things. This I write to the whole Lagrangian, contains a lot of terms, but in particular contain one term which I'll comment later on. So this improvement of the energy momentum tensor leads in the Lagrangian to higher derivative terms. One of them is of this type, Riemann coupling to this field strength FF. M is the mass of this massive fields. Actually, this is the full Lagrangian we find, quadratic in massive fields. It's a Lagrangian which contains, now you take this Lagrangian for Rarita-Schwinger, for Proca, for Pauli fields, you couple it now to supergravity, so that's why you see this covariant derivative. Now you couple it to the usual gravity, you couple it also to the usual gravitino, so it's a locally supersymmetric Lagrangian. And you see also here the term coming from this improvement that we had before. So these are terms which contain, in particular, higher derivative couplings of this type, RFF, plus coupling of the Riemann tensor to these two massive spin-2 fields, and there are various terms. So the first result is that taking the minimal supersymmetry, the usual supersymmetry transformations lead to a Lagrangian. You started just with spin-2, you try to couple supergravity, in fact, automatically higher derivative terms. It's a bit strange. Secondly, I'll argue that these higher derivative terms are potentially dangerous, and I'll try to comment on this. But let me now change a little bit the perspective and discuss, like people discuss in this massive gravity or big gravity theories, the issue of the unitarity. So what is the cutoff of such a theory? It is known that, so I'm taking two massive spin-2, and you exchange here all possible spin-2, spin-1, spin-0, what we have in this theory. I remind you that if you take the Pauli fields, if you just couple it naively to gravity, you find an amplitude which goes like s to the 5 in the high energy limit, s to infinity fixed angle. If you take the this DRGT massive gravity or the big gravity Hassan-Rosen, which are those three, you find S cubed. That's the best you can find. This means that all of these theories have a cutoff, a natural cutoff, which is below the Planck scales, including these ones. So these are at best effective theories. You cannot extrapolate up to the Planck scales. So we did the same exercise for our Lagrangian. So the naive expectation would be something like s to the 5, because that's what will happen. That's the usual kind of behavior. There was an argument in the paper by Paltin collaborators that if you take a massive spin-2 in the Regge limit s goes to infinity t fixed, the amplitude cannot go better than s cubed. Now, in our case, we have the, of course, what appears in these vertices is the energy momentum tensor of these massive fields coupling to, for example, to the graviton. And you have the usual energy momentum tensor plus this high energy, plus this higher derivative term. Now, what is this higher derivative term is doing? Well, this is not a higher derivatives term in this case for the graviton, but for the other exchanges there is. It changes the growing from s to the 5 to s to the 4. So it's in between this the gravity and the usual Pauli fields. Supersymmetry does help a little bit, but it brings you to s to the 4, not s cubed. You could try other things which I'll not discuss, but that's so this theory also has a cutoff, of course, has a cutoff below the Planck scale. And now you can ask yourself, what is the connection between this theory and, let's say, either Kaluza-Klein or string theory? Now, it turns out that this coupling that you see here, that I wrote before here, for example, this coupling, Riemann, two massive spin 2, something like that was computed for a specific spins 2 state from string theory, from the first oscillator for the open string. And we found that our result matches precisely what they computed. This was a paper by Lust, Dieter Lust and Stieberger and Mark Urmas-Lumi. So we found exactly the coupling that they found in the string theory context, in which what they did is to take one massive particle from the string spectrum. It's not a Kaluza-Klein, it's a string state, and two states of this and one gravitor, massless gravitor. The second, so it seems that what we have, and by the way, I can say it right away. If you take a Kaluza-Klein theory 5 dimension, the usual, let's say, supergravity 5 dimension, you put it on a circle, you don't find higher derivatives, of course. So this is not a Kaluza-Klein truncation, if you want. It is more like taking this massive Regge state and you couple it with supergravity. Even if the way we did it is purely field theoretical, by just personalizing the coupling of spin 2 to gravity. That's the way we did it, but that's what we found.
But why supersymmetry is helping? Because the fermions don't enter.
I'm sorry?
Why supersymmetry is helping you if the fermions are not entering at all?
For
Say
the
supersymmetry
amplitude behavior?
Yeah, exactly.
Because by supersymmetry, you found in this Lagrangian, for example, the energy momentum tensor also contains terms like this, for example. So the energy momentum tensor, or if you want the Lagrangian itself, if you see it here, Lagrangian itself has the terms like this times this by supersymmetry. Supersymmetrizing this coupling forced us to add these terms here by supersymmetry, but which contains bosonic pieces, purely bosonic pieces. So the coupling of the massive spin 2 with the graviton is not the usual one in Pauli fields. It's different because of this one.
Two terms and they cancel.
So this cancel the s to the 5 in Pauli fields. Yeah. Actually, if you take the longitudinal, you find this cubed. But S4 comes from helicity 1, not helicity 0. Something else which is more worrisome, if you want, is that this Lagrangian contains something like this. Riemann field strength for this massive P1. Now, we don't have a proof, but there was a paper by these people, Maldassena, Giboidov, Camagno, and Edelstein, which discuss this for massless gauge fields. And if for massless gauge field and more than 4 dimensions, strictly speaking, they show that this, if you put such a term in shock wave, in a shock wave background, this generates a potential violation of causality for any sign of this coupling. Now, they did it more than 4 dimensions for massless gauge field. We believe that their arguments apply here, but it's not 100% sure. But there is a potential violation of causality in Lagrangian because of this term. Now, if we really believe that this generates a violation of causality, then it means that the only way this theory really makes sense is to say that you have to add the tower of higher spin fields. In other words, this massive spin 2, if you see it as from a string theory point of view, you would say it's obvious because this describes the Lagrangian of a massive spin 2 from a string theory, and of course, string theory without the whole tower makes it's not consistent, of course.
I mean, but you can do it by time delay, but you can also do it by amplitude. This is very related to what I was talking here. You get the same time delay or doing by amplitude to see you violate causality. And this depends on the size of the coefficient. Size of the coefficient related with the scale at which the higher spin should appear. This is a relation 1-to-1 correspond.
In this case, I don't.
Exactly the same I was showing.
Okay, okay. Here, in this case, they say that for any sign you get problems with causality, but their argument did not work directly for dimension, and yeah.
No, yeah, the unit has spin, yes, but what is the scale where you need it? This is the point. You could generate this by integrating out fermions.
That's
not a problem. The only thing is that this bound tells you where the fermions will appear. It's not a problem to add this thing by itself. I mean, it's only that the size is related with the higher speed.
Yeah, okay, here we got it just by supersymmetrization, so we don't have.
Question is the size. What is the size in front of this?
1/m². This was mass.
The mass of the guy.
Yeah, the mass of this guy is massive, yeah. It's 1/m².
So this will tell you where the higher spin must appear.
Exactly. So I believe the higher spin should appear there.
There.
There, yeah. So if I take this seriously, it means that the cutoff of this theory is not this cutoff of this what people call the lambda 4, lambda 5, but it's the mass of the particle. Right. Which from the point of view of string theory is not so crazy, it's not surprising. Okay, if we believe all this, it's kind of evidence for this string Lampos principle, what people call string Lampos principle in 4 dimension and for minimal supersymmetry. In which sense? In the following sense that the Lagrangian we found was unique, and it precisely matches with the one coming from a string theory. If we wouldn't have matched with the one from string theory, it would have been a problem, of course. And we don't have any free parameters. So in some sense, taking minimal supersymmetry and believing that you should be able to describe massive spin-2 fields in this case, compatible with supersymmetry, tells you that the only solution is the one which is realized in string theory, even if you have minimal supersymmetry. So that's a kind of an interesting result, I believe. Now, if I have 5 minutes, maybe I just make some comments about how comes that this theory is not really the same as the Kaluza-Klein one. The argument goes as follows. Of course, we can start in 5 dimensions with a supergravity, let's say pure supergravity 5 dimensions, so which contains a gauge field, metric, and the 5-dimensional gravitino. You can compactify, let's say, on an orbifold to reduce supersymmetry to n = 1. You have Kaluza-Klein analog of this massive multiplet that I discussed before. You have this 4-dimensional Carol multiplet, if you want, that which contains the radius of the circle in particular. And of course, the usual supergravity multiplet, right? In this case, by the way, the way we wrote the Lagrangian is using this multiplet in which, if you want to use the unitary gauge, for example, this is, of course, 5 degrees of freedom, which contains the Higgs mechanism, a gauge field, and a scalar. But the way we wrote the Lagrangian, we wrote in the unitary gauge by putting these Stuckelberg fields to 0, if you want. So that's this would be the Stuckelberg massive spin-2. Okay, so this is the gravitons, this is the spin 1, spin 0, and this is the Stuckelberg that we really use to write our Lagrangian. Now, if you take a Kaluza-Klein theory, and if you want to write a Lagrangian truncated to one mode, you have to keep the unitary gauge. You work in the unitary gauge, you have to preserve the unitary gauge, which means that you have to accompany the supersymmetry transformations by diffeomorphism transformations along the circle. And this means that you have to use different supersymmetry transformations, not the one I use there. The supersymmetry transformation I use there is the naive one. But if you want to work in the unitary gauges Kaluza-Klein theory, you have to work with a different supersymmetry transformations. So that's why what we found was not the Kaluza-Klein, if you want, but it was something else, which is directly something which exists in string theory. Okay. Maybe just a last comment. So there are 2 ways to talk about decoupling with massive spin-2. One of them is to take some string oscillator, couple it to gravity. In this case, it turns out the SUSY transformations are the naive ones, the ones I wrote. These are the naive SUSY transformations. And then if you try to take the mass to 0, of course, you go to so-called tensionless limit of string theory, so the whole string states become massless. And the other way is the Kaluza-Klein realization, which you take Kaluza-Klein tower, you couple it to gravity. And of course, again, if you take the limit when the mass goes to 0, you find the compactification limit. And we found this one. This one certainly exists, of course. It would be nice to show that there is nothing else. There is no third alternative. It's not easy, technically speaking, but it should be possible. So, these are my conclusions. So we did by the old methods, the Neutron methods, we find the coupling of the massive spin to multiplet to 1d for supergravity. And strangely enough, we didn't find the Kaluza-Klein theory, but we found a coupling of, if you want something which contains high derivative terms, which precisely matches the Lagrangian you would find by taking the coupling the massive spin to multiplet in string theory to supergravity and truncating anything else. You have higher derivative terms in this case. Of course, these are not surprising from a string theory point of view. The interpretation of our result is that this theory has a cutoff at the mass. You have to really add immediately all the tower in order for theory to be fully consistent. And this will eliminate all kind of problems like causality issues if they really exist, because again, we don't have a full proof that this has a problem. We don't have a fully nonlinear Lagrangian in this massive field. We are restricted to the quadratic order, so we cannot really address yet what happens with the ghosts, if there are ghosts or not. Just my only phenomenological comment is that if you probably realize that these fields are coming into pairs, so this object is stable. So this could be one of these massive spin 2 dark matter candidate that is discussed in phenomenological literature. Thank you.
Very much, Emilian. Any questions?
Is it possible to embed that in extended supergravity that's spontaneously broken to n equals to 1?
Certainly it's possible. The way we did it, of course, it becomes more involved. You have to take these multiplets of extended supergravity. It should be possible. But our logic was that since even with one supersymmetry, we found these higher derivative terms, and this result presumably, by the way, the string paper I was describing was just usual string theory. They had full supersymmetry, of course.
So it means that the graviton can, the H mu nu can get a mass through Higgs mechanism? If you do
Well, you know, in string theory, you see directly in the broken phase, if you want, is the Supergravity phase. I mean, you don't have the Higgs mechanism to get the Regge masses in string theory. So it's directly in the Stuckelberg phase, in the broken phase. And yeah, I don't know how to do a Higgs mechanism. Yeah.
It works. Yeah. So it's cool the massive 2 spin field could be a dark matter candidate. Also, a tower of massive 2 spin fields could be a dark matter candidate, but that depends on the scaling relations with the just how the heavier modes are decaying. And it seems like one of the things that the sort of program of work could tell you is kind of how those scaling relations work.
From this point of view, the best would be to take a 5-dimensional Kaluza-Klein theory and go to 4-dimensional with tower. This one is really a string state, and it's more complicated to use this one than the Kaluza-Klein theory, I believe. Yeah.
Okay, is that a question? And let's thank Emilian.
The last speaker. Maybe you should really thank the organizers, Keith, who just left, Antonio.
So that ends the talk, but before we formally close the workshop, as you know, a lot of work goes into organizing the workshop.
I think I wanted to first actually thank all the participants.
I was gonna get to Well, as you know, that a lot of work goes into the organization, and I'm sure